into three major sections. So first off, I'm gonna introduce hardware accelerated tracing technologies in general, explain what they do, how they fit in with other tools, and what some of their use cases might be. I'm then going to move on to the actual implementation that we did for managing, interacting, and decoding traces generated by hardware tracing devices in FreeBSD. And the last section is going to be a case study of adding support for a specific hardware tracing technology to the newly written hardware tracing framework. So this talk is going to essentially be yet another talk about a new observability tool that's been recently added to FreeBSD and that we can leverage for advanced performance analysis and advanced debugging. So before I explain what this technology does, I will take some time to explain how this fits in with other observability tools that we already have. So as you're probably aware, we have a whole array of observability tools available in the source tree, ranging from simple tools that specialize in giving relatively straightforward answers to queries for specific subsystems. So things like PS, procstat, fstat, the list goes on. Those are great if you want to, just find out what's going on at a high level in a specific subsystem. But eventually, you might end up needing something more flexible, something that's able to answer questions about arbitrary parts of the system, which is where software-based tracing systems often come in. So systems like dtrace, eBPF are extremely flexible, are extremely useful. We all love them, we all use them. But they do have some drawbacks that don't make them a perfect fit for all use cases. So those of you who have attended BSDCan in 2022, I had the wrong year in the quote, might remember attending a talk that was dealing with the performance or exploring the performance overhead of the tracing software-based tracing technologies on FreeBSD and Linux. So Mateusz Piotrowski conducted a performance analysis of both dtrace and eBPF on Linux, and the benchmarking results found that indeed, as expected, there's a oftentimes significant performance overhead that these tools introduce. Furthermore, not all parts of the system are equally instrumentable. So instrumenting certain parts of the kernel or certain processes might lead to system instability, which is something that you don't want to see when tracing a system and trying to find out what's going on. So the other popular category of observability tools that you often reach for are sampling profiles. So, which often includes things like performance monitoring counters. These are great for giving you a thorough statistical overview of what your program is doing during its lifetime, and providing information about how many events, the certain microarchitectural events the program triggered. So for instance, how many times there was a last level cache miss, things like that. But these tools still don't give you a good overview of what's happening at the instruction level granularity, right? So this is where hardware tracing technologies come in. Hardware tracing devices are designed to collect detailed information about the execution of your software on a given CPU core and output that information into DRAM using a highly compressed format. So the main advantage of this is that now you have a complete overview of let's say a given function snippet or just a given program. You can find out exactly which functions were taken, which branches were taken. You often have timing information available, which makes these technologies really powerful in debugging, let's say, latency issues and things like that. So we'll move on to some other cases a bit further on. So the advantage of this being implemented in hardware obviously means that you have low overhead when generating these traces. And the other big benefit is you don't have to instrument anything. You just kick the device, it starts tracing, doing its thing. Once you're satisfied with the data you collected, you just stop it and analyze the data offline. So of course, there are downsides. Yeah. First off, these devices are not ubiquitous. They're not present on every platform. The most widespread of these technologies is the Intel's processor trace technology, yet it's been available for 10-ish years. ARM systems have some tracing technologies built in, but as I said, that's about it. The other, possibly the biggest downside, is that this tracing generates a lot of data. So we're talking about magnitude, several hundred megabytes a second if you're tracing some program that generates a lot of microarchitectural events. So you oftentimes end up having to sift through very large decoded traces, or you just have to focus on a certain snippet of the system and analyze that. So as I'd mentioned, some of the use cases that this technology handles very well is debugging latency issues in short-lived, latency issues in general, but especially in short-lived pieces of code. So hardware tracing technologies can generate information about wall clock time, about the cycles that were cycles elapsed between different packets. So you can use this to find out what's going on in a very short snippet of code, which is necessary if you're building any sort of high-performance application. Right? These traces also make debugging easier because now, in addition, so if you run a program, it crashes, and you have tracing enabled. Now, in addition to the core dump, you have a complete trace of control flow that led up to the crash. So more useful info to find out what's going on behind the scenes. Right? And a somewhat unorthodox, more research-oriented application is real-time security analysis. So several researchers took advantage of the fact that they can generate very precise execution traces with low overhead, and used several tracing technologies to enforce certain mitigations or security policies. For instance, one of the more notable papers is the one that's quoted here. These researchers used Intel's processor trace technology to implement a mitigation scheme for guarding against code reuse attacks. So now we can switch on to the FreeBSD side of things. So as I said, this is a fairly recent effort. And this whole system was implemented in two parts. So the first part is the in-kernel memory, in-kernel hardware tracing framework that interacts with specific platform-specific tracing devices, manages and creates tracing sessions, does all sorts of wonderful things, but we'll get into that more later. And the other part is the actual user space tool that will start tracing for a given process, collect the data, and decode those traces into something more human-friendly, human-friendly output. So the framework itself is an event-driven framework, meaning that the framework ingests certain events from certain parts of the kernel and forwards those events back to user space so the decoder can function properly, pick up the data, decode it, and so on. It was originally authored by Ruslan Bukin as a part of his effort to add support for the ARM core side tracing device, obviously on ARM. It was since extended to support other tracing technologies, and it allows end users to trace arbitrary processes, the ones that they can start on, to be specific, and to trace basically any piece of code that's running in kernel space. So these technologies are, random order. ARM's core side tracing technology, which is a separate device. ARM's statistical profiling extensions. This work was done by Zachary Leaf from ARM, and the Intel processor trace backend, which was bestowed upon me. So I'll briefly touch upon the tool part, the user space part here. So the HWT8 tool is used to create processes or attach to an existing process, interact with the hardware tracing framework to start generating a execution trace for these processes, and then collect the data and decode it into a human-friendly output. So the tool can run in two modes. The first one being thread mode, which is synonymous with user space process tracing. But in this mode, when you launch a process, every thread that's spawned by this process gets its own execution trace generated. So you can decode practically everything that's been going on. CPU mode is basically shorthand for tracing the kernel. You could theoretically do that for any piece of code that's running in kernel mode, but for practical reasons, we limit this only to filtered selective tracing of certain functions within the kernel. So yeah, I previously mentioned that these technologies generate a lot of data. So fortunately, we do have ways that you can filter these or just zoom in on a specific part of the code. So the -f flag allows you to specify a arbitrary symbol name, and provided that it exists in the target executable, the tracing hardware will only generate the execution trace for that specific address range. You can do the same for executable images. So for instance, you're tracing a program and you want to see what it's doing in libc, for instance. You can filter the entire trace just to output things related to libc. And you can also prune filter things by individual, so just inspecting a log for a certain thread. So I mentioned that the tool also does the decoding of certain, decodes the traces into certain human-friendly information types. So we do have a way of letting the user provide its, basically the output columns that they want to see decoded. Some of these, so similar to how you'd use, I think, the -O flag in the PS utility. So notable column outputs include, obviously, having a way of associating the current instruction pointer that generated the trace with its corresponding ELF symbol. Obviously doing the same for the executable image name, and some experimental, not yet fully committed feature is it provides you a way of disassembling the actual instruction that generated the trace. So you can get a live disassembly output as you trace. So this snippet is just here to give you a taste of how the output of this tool looks like and how the tool works in general. So this snippet just is a result of launching tracing for the uname program. The decoder will, the user space tool will start the process, fetch the incoming data, and as the data starts to trickle in, it will start decoding it and producing human-friendly output. Right? So this is kind of a high-level overview of high-level component diagram of the whole system, if you will. So on the left-hand side, we have the kernel space components. On the right-hand side, we have the user space components, or just the decoder, in essence. So the actual framework sits between platform drivers or tracing devices and the rest of the kernel. And as I said, the framework is tasked with creating, managing, and multiplexing, creating and managing tracing sessions and multiplexing access to the underlying tracing devices. It also has to ingest certain events from other parts of the kernel in order to make sure that the decoder trace is correct and that the decoder is able to function properly. I'll get more into those events a bit later. So the decoder itself is tasked with initializing the actual tracing. Once it does do so, the HWT framework will just call in the appropriate methods in the platform driver. Once the tracing device starts doing its thing, it's going to start filling up this tracing buffer that's mapped, also mapped into the decoder's address space, right? So the decoder will then collect this tracing data and combine it with actual executable images that were responsible for generating that trace into the output that you saw in the previous snippet. So that's the high-level overview of things. So I had mentioned that we need to look out for certain events that are generated by the rest of the kernel. So These things include scheduling events, any address space layout change of the process, we have to react to those. So for scheduling events, if we're tracing a process and a thread gets switched, every time a thread of the trace process gets switched in to a certain CPU core, we obviously have to enable the tracing hardware, right? Once the thread gets kicked off the CPU core, we also have to disable it. Otherwise, we end up tracing everything that's running on that core, which is something we don't want to do, right? Every time a new thread gets created, we have to let the user space decoder know that this happened and update its internal data structure so that the decoding process can, move on as planned. M-mapping objects. So any M-mapped object might have executable code. We have to take all .txt sections into account and let the decoder pick them up from the corresponding binary so that the trace can be fully decoded in user space. And obviously, if the program executes a whole new image, the decoder has to drop everything and load in the new process. Right? So all of these tracing operations are exposed using via a character device. So /HWT controls the initial steps for starting and allocating tracing sessions. And in general, the whole framework pretty much relies on two really important types of buffers. So the first one being the actual tracing buffer. So the memory region where your CPU is going to emit the tracing data or the packets. So in tracing modes, every CPU gets its own tracing buffer, every thread gets its own tracing buffer. That way, those generated traces don't mix in a single buffer, which would have been a nightmare and impossible to decode. Right? And the second thing is the so-called event or record buffer. So this basically provides us a way of taking all of these events that are picked up by various hooks across the kernel and signaling the user space, basically forwarding all of these events to user space and letting the user space know that, hey, the device has generated new data starting from this offset, go, collect it, pick it up, do your thing. And yeah, obviously we've covered this. So this is just to showcase the actual structure that gets sent to user space. It's just a discriminator or tagged union, whatever term you prefer. But it nicely showcases all of the different types of records that are in the system. So practically all of these records are generated by kernel hooks. So those are the events that we have to kind of look out for when we're tracing. And this is by far the most common type of record, which is basically generated by the hardware when there's new tracing data available. So the user space can react to this, pick up new data, and decode it. So the actual tracing operations from user space are kind of summarized by this sequence diagram. So a user tool will initiate tracing sessions by signaling the character device that it wants to allocate, it wants to start a new tracing session. So under the hood, the hardware tracing framework will allocate a tracing context, create the corresponding process, or find it if it's not already there, and it will create a character device for that specific tracing session. So in this case, if we're tracing a user space process, it's session ID 0 and thread 0. At that point, the user space tool only interacts with the corresponding thread, the corresponding tracing session's character device. So doing an allocate operation with HWTI as start tells the hardware tracing framework to start generating tracing logs for the corresponding session, which means that it's basically going to defer to the platform driver. So it's going to use this to configure the hardware and to kick off the tracing. And at that point, the user space tool indefinitely loops in this here call. Just basically wakes up, waits for incoming data, picks it up and processes it. So the hardware tracing framework abstracts So when we're talking about specific technologies within the hardware tracing framework, we usually refer to them as backends. So a backend is basically just an abstraction of a certain hardware tracing device that's basically described by this here interface. So aside from the usual, we have to actually initialize and deinitialize the hardware, make sure that the driver discovers proper support for the hardware, configure it. We also have the common operation here that basically just kicks off the hardware on a given CPU core. So, however, in certain systems, those tracing devices are built into the actual core. So you cannot just go blindly using these ones because there's no guarantee that they might be triggered on the target core. So for these backends, we have to do a relatively complex solving and dance that involves IPIs and a short but kind of complicated protocol that makes sure that all of these tracing devices only start sending data when every single core was initialized, right? And also the individual platform driver has to have a way of embedding some of its platform-specific metadata into individual thread structures, so that, it can actually pick up and continue tracing those threads as they get pulled in and out of a CPU core. And we have a similar interface in the user space tool, which is basically just an interface that lets the user space tool call into the platform-specific layer so that the platform-specific decoder can do its thing, process a buffer, so it can pick up new tracing buffers. Every time we mmap something, we have to scan the mapped object for executable code. So the decoder has to be able to pick up these things as well. And you obviously have to be able to configure the device from the tool as well. Okay, so I think it's a good time to move on to a case study of the Intel processor trace technology. So I'm going to just provide a brief overview of what this is. So as expected, the Intel processor trace technology enables packetized logging of all sorts of information about software execution. So this obviously includes control flow information. So whether the last n unconditional branches were taken or not. This also was extended to include things like power management events. So every time a C state, a processor enters a C state or exits a C state, a packet is emitted into the tracing buffer. We also have fine-grained timing information. So packets containing that track wall clock time can be configured to be emitted into the tracing buffer, as well as packets that measure the cycle count that elapsed between the last two packets. So you have very fine-grained timing information at your disposal. And the last kind of notable thing that this technology allows you to do is to insert packets entirely from software. So this is done through a special instruction called ptwrite, and I'll showcase that a bit later. So fortunately, this technology does provide some form of trace filtering as well. So you can configure the hardware with up to 2 specific address ranges. So the tracing hardware will only generate an execution trace whenever the target instruction pointer is within those address ranges, which makes it convenient to trace, short functions, things like that. It also allows you to filter the trace based on the current privilege level in the processor, which is nice and also a prerequisite for the whole thread mode versus user mode or mode of operation that we have in the HWTA tool. And it can also, the filtering can also be configured to, filter on, to kick in when a specific page table pointer is present in the CR3 register. So the generated execution traces, the generated tracing log can be used to construct a complete exact execution trace of, of basically whatever your software did on that CPU core. But it's not, the tracing log on its own is not enough because it doesn't encode information about the process's address space layout at the time, since that would be mostly redundant, and this whole technology was geared to compress data as much as possible. So the decoder has to have access to the actual binaries that generated this trace. And it's also virtualizable with a big caveat that it's present only on some very recent CPUs, which of course doesn't include my laptop here. So this is an example of a very common packet that you can see in the generated tracing stream. This is the so-called taken or not taken packet. This packet essentially encodes information about whether the last n conditional branches were taken or not. So every bit in the packet is going to be set to 1 if the nth oldest conditional branch was taken, or 0 if it wasn't. So obviously every packet is prefixed with a packet header. This one is rather short in this case, and is always followed by a stop bit, so that the actual hardware can generate more compact or longer forms of the packet, depending on when the event was emitted. So this packet also comes in a longer form. As you can see, this one encodes up to, I think, 47 last branches. And the stop bit can be actually, so if the processor keeps trace of the recent branches that were taken, and if it has to emit the event prematurely, this stop bit will actually get moved, squeezed further down the packet if it wasn't entirely filled. Okay, so I'll want to some key implementation details of the actual driver that configures and starts tracing on the Intel PT hardware. So first off, the driver uses the xsave instruction set to basically toggle and manage everything related around the tracing hardware itself. So the xsave/xrestore functions, instructions provide us a way of managing resources. Those mostly include model-specific registers related to specific software, specific features present on the CPU. What this means for the driver itself is that we can just easily pre-configure the set of the values of the model-specific registers within a certain buffer in memory, and we can load those values in with one single instruction. So this makes it super easy to cut down on the additional bookkeeping that the driver has to do, and it also starts the tracing hardware in one atomic operation. And it also, once we're finished, the thread gets kicked off a CPU. We have to be able to save those values somewhere. So this provides a really nifty way of doing so as well. The actual device has a very flexible way of configuring the tracing buffer using the so-called table of physical addresses, or TOPA for short, mechanism. The TOPA table is essentially just a linked list of tables that the processor fills in as it uses to fill in the pre-allocated regions of the buffer. So in this case, part of what makes this technology so fast is the fact that tracing data gets written out directly to physical memory. So it bypasses the virtual memory subsystem, no caching, just asynchronously writes into physical memory and lets the user space cope with the fact that it's just doing its thing here. These TOPA table entries also provide us a way of generating interrupts when certain tracing regions get filled. So this kind of provides a synchronization point for user space and generates basically a buffer event that we have to bounce out to user space for the decoder to pick up the data and decode it. Right? So this is the layout of a single TOPA table entry. The upper bits here encode the actual address of the output region. You can also configure the region to be in, the regions may come in various sizes. So these range from 4K pages up to 128 megabyte regions, which, if you're generating a lot of data, might be the thing you want to do instead of having just a bunch of 4K entries. And the last three fields here provide a way of signaling, basically modifying the CPU's behavior once it fills up those specific output regions. So if the stop bit is pulled up, the processor will simply deactivate the tracing device once the target region has been filled, right? Which is useful if you want to collect a short or just fill up the entire buffer and not collect any more data. But also, as I previously mentioned, you can configure it to schedule a performance monitoring interrupt. So this way you can let the user space know that there's more data available. And if the last bit is pulled up, the processor will treat this as a pointer to the next table. We just load it into the corresponding model-specific registers and continue doing its thing, right? So this is how we end up configuring the table in the driver. It doesn't quite take advantage of the flexibility of the format, but we just pre-allocate, the hardware tracing framework pre-allocates a buffer of a given size. And we basically just have one entry for every single 4K page. We tag every single 4K page with a topa int field. And last but not least, we make sure that this becomes a circular buffer by tagging the last entry with topa end and pointing it to the top of the table. So the CPU can keep on writing indefinitely. This here comment is something that I'm sure will bite me sometime in the future. It hasn't occurred yet. But ideally, you don't want to have an interrupt generated for every single 4K page that gets filled. It's like tracing, the amount of tracing data generated when you're tracing a short function is not the same, obviously, as when you're generating tracing information for the whole process, right? But currently, you don't have a way of sort of adaptively, strategically pulling up these topa int bits on specific places, which is something that we'll probably implement sometime in the future. But yeah, generating too much interrupts will also kind of defeat the whole low overhead purpose of the whole tracing, the hardware tracing devices. So once a performance monitoring interrupt does come in, we have to transform it into a buffer event, right? And bounce the event back to user space. So once we've made sure that this interrupt was indeed generated by the tracing hardware and that the tracing session is active on this core, we have to obviously switch off the hardware because we don't want to generate a trace log for this here snippet. And we read, basically update, create a buffer record with the last offset that the CPU has written to. And we schedule off another thread that's going to allocate the actual buffer structure and wake up the user space decoder to do its thing. And yeah, last but not least, if the tracing is still going on, if the user hasn't disabled the tracing, we have to rearm the local APEC vector entry and start the tracing again. Okay, we have reached the demo. That was slightly faster than I'd anticipated. Okay, so in this case, let me showcase how this looks like for tracing a random user space binary. So as you can see, yeah, I forgot to print out the actual columns. I have to implement that. But as you can see, we have started generating the trace after the process was kicked off. And the first column represents the actual offset into the tracing log that generated these here events. The second column is the ID of the tracing unit, if you will. So basically, whether thread 1, 0, or n generated this trace. The third column represents the offset into the respective executable image, right? And the last column is the actual instruction pointer that we captured during the trace. So at one point, I'll have to switch to a custom-built uname that has symbols enabled. That shouldn't be a problem. So at one point, I had mentioned that this is the default decoder output. So using the -o flag, you can tweak the output as to your heart's content. So if we start tracing like this, you're just going to have the instruction pointer and the corresponding image. Right? If we do end up adding something like this, you can now see that we've started decoding the actual instructions that were involved in generating this trace. This is a slightly experimental feature. I haven't actually settled on a decoding library yet. We'll see which one fits better. But yeah, the dash O flag lets you be flexible with the output that you want to generate. So obviously, I have been truncating the output for this whole time, because if I do this, it goes on for a while, right? There are a lot of things going on. So one of the things that you might want to do is having a way of filtering the actual thing. And we can do this so it's a bit unwieldy because obviously I had to make sure that this symbol table is present here, that the debugging symbols are present. The dash I flag basically triggers, as I said, triggers filtering for a specific executable image. And if you pass the dash F flag, we can find out what's going on in uname's main. Not a lot. So it just ends up setting up the stack and calling, I think it's called print uname, the internal function. Fortunately, we can also trace this one. Okay, so that's ignore the broken output. That's also on my to-do list. But anyhow, you can actually zoom in on a specific snippet, see what's going on, and we will probably end up adding some form of timing-related information in the future. But yeah, this is what we have for now. And to cap things off, you can also do this for, as I said, kernel functions. So the symbol resolution is a bit broken right now, so you get all sorts of weird non-related symbols within the trace. But basically, we can zoom in on a specific CPU kernel function and see what's going on. And you can do it online as well. So. Generating a lot more data. Well, okay, so this here specific snippet, of course, the one that says CPU switch is what CPU switch was indeed doing. And once I figure out what's causing the other entries to appear in the trace, it'll be a lot cleaner as well. Okay, so there was another part of this demo that I really wanted to showcase, but unfortunately my laptop's a bit too old, so it doesn't include support for the PT-write instruction. So as I said, Intel PT lets you output a tracing buffer, a tracing packet from user space software or kernel space software as well. And this is just basically a compiler built-in intrinsic that is lowered to the PT-write instruction. So this is what it would have looked like if I had support for the for the hardware. So basically, any single value that you pass to the PT-write instruction is going to be emitted within the actual tracing log, which makes it super useful to, if you want to do manual instrumenting with this technology, you can. It's low overhead. If the tracing hardware isn't active at the time this instruction is executed, it's effectively a no-op. Right? It still does, decrease the instruction cache efficiency, but yeah. So I'll just briefly touch upon the work that went into adding all of this that I just showcased. So first off, when I initially joined Ruslan's efforts for adding more devices to this framework, I quickly found out that we have a lot of things missing in the x86 specific code in FreeBSD. So the problem here is that the performance monitoring counter subsystem and this driver use the same interrupt line, which makes it a bit tricky to share if you don't have support for doing so. So we had to add a way of dynamically registering NMI handlers, making sure that we can also share the interrupt line. And also we were missing some crucial Xsafe related APIs, so things like discovering whether the processor supports this Xsafe feature or not, and lots of other x86 specific things that I'm not going to get into right now. And back when I first joined, HWT only supported the core side device. Well, the core side device is a bit of an oddball here because it doesn't generate interrupts. So the user space hardware has to constantly pull the corresponding register and use up a lot of CPU in the process. So we ended up adding a whole bunch of things to the HWT framework that makes sure that interrupt-driven devices can also properly function within the framework. Right? And then there's, of course, the driver itself with its accompanying user space bits, so the backend and the decoder. Okay, so a lot of work went into this, but we're still not quite there yet. The tool does work nicely, but aside from fixing certain minor bugs, and we have a wish list of features that we want to see. So for instance, you probably noticed that I have been tracing all of these things online. So that's fine, but the decoding process is a bit slow, and it can also, consume a fair chunk of your CPU. So ideally, what you want to be able to do is kick off a tracing session, save all of the related data into a single file, and analyze it afterwards offline. So we do allow users to dump a raw tracing log, but as I said, on its own, that's not enough. We have to have a way of somehow encoding the information about the process's address layout before, since that's a crucial information that the decoder needs to to properly decode the trace. On a unrelated, sort of related feature that we have encountered is the processor event-based sampling support. So when interrupt-driven performance counters do their thing, they can often suffer from what is called a performance counter skid. So basically, when the counter overflows, an interrupt gets generated, but by the time the interrupt gets delivered to the core, the function that triggered the overflow might not be the same function that is picked up by the NMI handler. Fortunately, Intel does offer a way of remedying this, and more fortunately, this is a packetized format. So these events are outputted into a specific memory region in a packetized format, and of course, they have support for being for being emitted into an Intel PT tracing buffer. And the Intel PT subsystem does have the corresponding packet definitions to go along with those. However, I haven't quite figured out the logistics of this since it does overlap with the performance counter subsystem. So that's pending. We're going to get to that eventually, but yeah. And last, of course, probably the most important thing for a observability tool, post-processing. Right? What I have shown you here is fine, but it might not be enough if you want to buckle down and analyze performance or latency issues within very specific functions or snippets of code. So we'll have to figure out to add which post-processing options we want to add a bit later on. And also we have to look if we can integrate with existing tools. So LLDB, and both LLDB and GDB have a way of combining the generated tracing log with the actual debugging session. I think one of them even offers a way of replaying the actual instructions with this. And also I think the flame graph tool also can be coerced into generating high resolution flame graphs with this technology as well. Okay, so that's time to wrap things up. Hopefully I'm not much over time. Okay, so these are some of the notable reviews that you can look at. Come by, say hi, maybe leave a couple of comments. The actual driver has been accepted, but there's no point in landing it before these things go into the tree because they're obviously a dependency, right? So I'd like to thank everybody who helped review these patches in any way, shape, or form. So Mark J, AVG, Gallatin, more people that I'm sure I don't remember now. And a special thanks to Konstantin, who has provided invaluable feedback for the x86 specific bits and the PT driver itself. So yeah, I guess that's the end of my talk. So I'm happy to take any questions you might have. Yeah, sure. Yeah.
Excuse me.
Oh, the mic's coming. Just
Microphone.
Yeah.
Can you stop and restart tracing from a single user space thread?
You can. So by stopping and tracing from a single user space thread, do you mean the thread that does the decoding, or the thread that's being traced?
The thread that is being traced.
Oh yeah, of course. That's the so it happens all of the time. The decoder can manually stop the tracing if it wishes to do so, but the trace stop/start thing occurs every time a thread gets put onto a single CPU or just kicked off during when the thread is scheduled, basically. So yeah, you can do that as well.
And can you switch context, so to speak? That means the whole buffer subsystem, that you have multiple of these for different sections of your user space code?
That's a good question and an idea for a nice feature. You cannot do that as well, unfortunately, at the time. So no, a single thread gets a single tracing buffer. So you cannot actually do filtering per thread, which is kind of a byproduct of the hardware and the way that we design certain things, but it can probably be built into the system quite easily. But yeah, good question.
Thanks.
Do you understand right that this infrastructure will collect only traces, like which instruction executed and which branches were taken or not taken?
Yeah.
But we're not getting any information about registers, about anything else?
So certain packets can carry information about registers. For instance, the PEBS packets can be configured to output a fairly detailed snapshot of the packet state that, of the microarchitectural state that actually was responsible for emitting that packet. I am not that sure about other packets, but aside from that, there's a ton of microarchitectural events that you can trace, a ton of architectural events that get emitted into the actual trace log. It's just that the tool doesn't have support for them yet. So.
But perhaps it's supposed to be called only by the PMC counters. But
Yes, exactly. But fortunately, this does have an option to be emitted into a PT tracing buffer. So it has its own PT packets, if you will. So it's fully compatible with one or the other, right?
yeah, but it's not triggered, not controlled by the PT. It should be controlled through the PMC. You need to set some sort of event in PMC.
Yeah. So you have to arm the actual counters before, right? That's one of the. But yeah, as far as detailed register information is concerned, this is the only thing I think that provides the register states themselves. Yeah. Well, if there are no more questions, thank you all for coming. introduce the whole thing. So if you have, I guess if you have the whole like the whole process, you could theoretically just want files or have a way of basically online, offline. Yeah, that's how quickly, so building works kind of, you can toggle individual ones. So for instance, obviously the take and take thing will just.
Is it not supposed to be? I know when he disconnected his laptop, it turned green.
Kind of
Computer.
It says display port though.
So as I said, everything is single.
That should work. It's not. Of course, this happens right now. Was this? I wasn't paying attention. I went outside when he. Was this laptop the presentation was being given? Oh. Okay.
So I know it works. I've tried it.
I forgot what happened.
Well, I mean,
back in time.
macOS. Oh yeah, yeah. I have.
Are you presenting the next talk? I'm.
Yeah, because it's
I.
actual.
Okay. Pay for it. Try that one.
Find out typing this on your.
Okay. Let me get help. You got 20 minutes. You're good. Don't worry. Oh wait. Go back to your slides. Just did something.
Architecting software is
Hero.
working with a capability like model of the way that file systems work. That is a good thing. Glad that this is just for but you're wrong. But everything else I said in your the reality is like, okay. As we've seen with Patrick, right, it's a lot of work to get these people to software, and it's OpenBSD goes to something nobody.
I start? Okay, so hello. I'm Christos. Maybe some of you know me at this point because I come to every single conference. And today I'm going to be talking about sound on FreeBSD, how it works, how we do sound on FreeBSD. Even though the title says Sound 4, which is a basic kernel module, I'm going to give a brief overview of mostly everything, but with a focus on the actual Sound 4 kernel module. So yeah, even George Orwell used it, by the way. That's a real picture. So who are... okay, so something is wrong with the PDF. So who am I? I'm a FreeBSD committer since some year, I don't know, 2023. Yeah, I currently contract for the foundation to work on audio. Maybe I shouldn't do that because I keep producing too many bugs while fixing some. And so, yeah, let's start. So the talk is going to go, as I said, how does sound travel from application to your ears? The sound, well, here, the sound card, but it's eventually your ears. And vice versa. How can you record sound and take it from the microphone to the application? And so we're going to cover the various layers we have, except the hardware ones. Userland, Sound 4, again, the main sound code, and then the device drivers. We're going to discuss some improvements, just mention them. And if I have time, I will just spend a minute talking about why you might want to use FreeBSD for music, even though probably none of you has thought about this before, maybe one or two. So this is the, let's say, very high-level control flow of how sound works. If you notice, the arrows are not all the same. Some arrows send data to the device, eventually speakers. Some others take data from the sound card and go up to the process. So playback, recording. And some processes can do both. For example, you can record sound and play sound, like, yeah, Firefox or whatever. So this is the userland part, the one that is highlighted in blue. We have the processes. This could be MPV, Firefox, OBS, and processes interact with the character devices, Dev DSP. I guess you've seen them. So let's see how this works. Okay, let me just continue with the control flow. So we have Sound 4. So the devices talk to Sound 4. Sound 4 talks with the device driver. The driver talks with the sound card, and then the peripherals. So userland, yeah, okay. So userland, how it works is really simple. You just use basic syscalls, open, close, read, which interact with, so the userland interacts with the open sound system, OSS. It's a kind of old API, but it's stable, it works. It has some problems, but if you compare it to ALSA or the Windows API, you'll see that it's really, really more elegant. So these are all the possible syscalls a user program can use to interact with the sound. You have open, close, well, open and close the device. Read, write for recording and playing audio. I/O control, you can change sample rates, ask the name of the sound card, change format, do volume control, buffer sizes. Then we have select and poll, just in non-blocking mode. When the device is ready to receive or send data, you get an event. And mmap is quite interesting. It's actively discouraged by the official developers of OSS, and also by me. People use it because you get direct I/O, somewhat direct I/O with the sound card, and supposedly you get better, lower latencies, but it's so complicated to do it correctly that most likely you're going to make bugs and not sound come out of your speaker. So there are applications that use it, maybe high-end scientific applications or some games might want to use this, but with these you are absolutely fine. So for anyone interested, I can share the slides after. This is the most basic program you can write with OSS. This is just takes audio from your microphone and plays it back to the speaker. So you open the device. So DevDSP is the default device. It's not really anything crazy. You just open the device with read-write. You set the hardware channels that you want to sample from. So let's say I have a sound card there in my bag that has 2 hardware channels for sampling, so stereo. But here we choose mono. Then you choose the sample format, 16-bit lower endian. Then you choose the sample rate, that's a classic one. And then you just, in a for loop, you read one sample from your microphone, you play it back to the speakers, and then you close the device. That's it. So very simple. You shouldn't write applications like this, but just to showcase how you can get started just with, how many is it, 10 lines of code. So now we'll move on to the more interesting stuff, the main kernel code, which does. So you might have seen it mentioned as PCM. That's mostly for historical reasons and also because the directory that the code is stored is called PCM. So this is just a generic layer for drivers, device drivers to attach to. So we have many drivers, USB sound cards for HDA sound cards, for other PCI sound cards, and all these attach to this layer so that we can have a nice unified interface. You access the same /dev/DSP device for any sound card. You don't really need to care what sound card it is. You just access it and it works. It also implements the OSS API. As I said, exposes the devices. We also have the mixer device. I'm going to talk a bit about it. It's not really interesting. It does channel and buffers handling. It has a processing chain, which is probably the most interesting part. I will talk about it. Sorry, I'm getting ahead of myself. It also has some sys controls. These ones, the hardware.sound, are just global sys controls that affect the whole sound system. And then you have the dev PCM ones that are separate for each device. And you can set sample rates there. You can see various properties, names, sample rates, equalizer, whatever. And then you have this third device, which just shows information about the current, all the sound cards, their channels, everything. So this is how the DSP thing works. So when you access one of these devices, these are your processes, you access the device, and then with using the CDEV-Priv framework, we can just assign channels to each device. So this one will go to proc 0, this one will to proc 1, this to proc 2. So when you have multiple processes that are accessing one device, you need to know which sample goes to which process. You cannot just dump all the sound to one process, or you need to somehow separate processes and work in a more organized way. So all those private structures, they have up to 2 channels. You can have, as you can see, you can either have one recording channel. So if you're just recording, you'll be assigned one recording channel. If you do both, you'll be assigned one recording, one playback. And if you're just doing playback, you'll have, one playback channel. So these are virtual channels, as you can see, which means we have virtual channels so that we can have up to infinite processes that can access the device at the same time. Because the sound card usually has 2 channels, right? Let's say. And it's not possible to access one channel, let's say the playback channel, with 100 processes at the same time. So we have an upper layer with virtual channels, and then we do the whole mixing, post-processing, and then we send it to the actual hardware to be played back. So Dev Mixer, I said it's not really interesting. It's used just for volume unmuting and muting. And recording source setting, it's not really needed anymore. It's just mostly a legacy feature. Even the manual says you could just not use it. But Mixer still uses it. So it's not worth to rewrite something that will eventually give us the same outcome. But it is there. You can use it. So we have the SND stat. This is, as I said again, just prints information about devices. You can use the cat command on this device and it will print out device names, what channels they have, what processes use them, and flags. And I would say, since there is this utility since 14.3 stable and current, you can just use this and it uses all the information from SND stat through the NVList interface it has. So you don't really need to access this anymore, I would say. You can just use this and you'll be fine. Also virtual-OSS and some other applications use those. So channels. So I mentioned before channels, virtual channels. What is all that even? So a channel is really just an organized way to receive and send, and to record and play audio. That's all. You have a buffer, you do stuff with this buffer, and you either send it back to the user LAN or you send it to the sound card. Really, that's it. Don't think of channels as in the actual hardware channels in the sound card. That's a different thing. So each channel has two buffers. One buffer that is, we call it software buffer in some places in the code, because it just interacts with mostly the sound for end user LAN. So if you write bytes to a buffer, you'll actually write here to this one. So we call it software buffer. Well, then at some point, this buffer is copied to the hardware buffer. After all the processing is done, we copy the secondary buffer to the primary one, and then we send sound to the driver, or we take sound from the driver. And now we have the processing chain. As I said, that's maybe the most interesting or more involved part of the whole thing. So processing chain means we can, in the kernel, we do sample rate and sample format conversions. So let's say you play an MP3 file, but the application converts this MP3 file to 16-bit format. But your sound card actually works with 32-bit format. Well, you cannot just send 16-bit PCM streams and expect your card to play. You'll not get the right result. So Sound 4 is responsible for taking any formats and converting them to what the card actually needs to receive. And also it does the same for rate. So we can do resampling. Let's say you give it 40,400, 14,000, oh Jesus, 14, what is the number even? 4? Yes, this, thank you. So you can convert this to, let's say, 96,000. If the card expects this format, you cannot just send it whatever. Yeah, so we do the conversions. We also do equalizer. It's quite hard to use right now, so it's there, but I would say, yeah, you need to know how to use it. We also do mixing, because we have many virtual channels, as I said, and each process writes its own sound. We need to combine all this to a single stream so that it's played by the card and you hear all the sounds at the same time. Otherwise, you would hear separate samples. So you need to combine all the samples, mix them together, and then it's ready to go to the sound card. We also do channel matrixing. This is, maybe some of you, more the audio people, may have seen, for example, you might have a setup in your house that is called like 5.1 channel sound. So if you remember from the previous program, the sample program I had, I used mono sound, or you could use stereo, let's say. But if your card actually works with 5.1, well, you cannot just send it stereo format. You need to convert this to a 5.1 stream, and then it's ready to go to the sound card. And the opposite is true. If you're recording, but from a, let's say, stereo card, and you want mono stream, then you have to take this stream, convert it to mono, and then it's ready to go to user land. And also volume control. I guess you all know what volume control is. So each channel has its own processing chain when it's created. It's not a global chain for everyone. So let's say that for one channel, we just need resampling. That's it. We don't need anything else. So this channel would just get the resampling part of the chain. Other channels may need matrixing, so they will get just the matrixing. Other mates needs all of that. So we give each channel their own processing chain, and this whole thing is triggered by the driver. It's not so. Let's say you have a USB card, and it reads, every few seconds or when it's ready, it needs to take samples and play them to the speaker and send them to the world, to the speaker, right? Or you're recording and when it's ready and it decides it wants to send those samples back to userland, then it will interrupt the channel with this function and then the whole processing will happen. And if you want, you can use again this command to dump the processing chain. You just run it, it will show every channel that is active for this sound card and it will print which parts of those chain you have. So is this understood even, or am I just rambling too much? So one thing that I think FreeBSD is very good at is low latencies. And this is why I'm going to talk later, why you might prefer it for music production. So latency, I guess, does any of you not know what latency in sound is? Okay, so we all know what latency is. So if you want, so all this processing, virtual channels, it causes overhead, right? And because we deal with sound and so if you, let's say you're a musician and you're recording and you need to have as low latencies as possible because you're playing guitar and you want to hear at the same time and you don't want to just hear what you're playing 1 second after because that's unusable. You cannot play like this. So you might need to have as low latencies as possible. So to do that, you can just start disabling stuff from your sound system. You can disable vChannels, for example, virtual channels, sorry. You can run this command nowadays, and that will just disable the virtual channels, but this means that when you access a device, only one process can access the device each time. As I said, we have virtual channels so that we can have multiple processes accessing them at the same time. If you disable them, well, you just give access only to one application at a time. You can also skip processing. You might see it as bit perfect. I know some people who are audio people will say, no, this is not exactly correct. I know, but it's for simplicity's sake. You can disable processing by some of the processing by enabling the bit perfect option. But if you want just a shorthand, I just have made this nice shorthand command. You can just, it has same defaults for getting as real time as possible. And you can also use the latency syscontrol, but there are more syscontrols by Sound4. The drivers also have their own syscontrols. So yeah, if you want after the talk, we can just look at each one of those individually because I will not have time to explain all of them. You can also use the Mac priority and real-time priority features to get even lower latencies. Like just give, let's say, your audio recording program real-time priority, but this will obviously cause CPU problems. You'll have more CPU wake-ups, hence more load on your computer, but you'll have lower latencies. So Florian Valpan actually has written a nice has some nice notes on using low latencies with Jack. I don't know if any of you has produced music. Probably you've used Jack. It's just an audio server that gives you low latencies. It's used by recording programs mostly. So yeah, you can go here and see what he has to say. It's really mostly this stuff, but in a more explained way. So drivers, now we go one step down the control flow. Well, drivers are, well, hardware drivers. They talk to the hardware. So let's say you have, okay, I have a sound card here. That's just a USB card. You connect it, so it attaches to this driver, the U audio driver, right? If you had some of you, well, most of you, who have laptops have integrated sound cards, so they attach to the HDA driver. It's like network interfaces. You have drivers for network interfaces. It's the same thing for audio cards. And yeah, so the drivers do communicate with the sound card. They do all the internal things, PCI, USB, yeah, all the stuff that drivers do. And they also talk with Sound4 to interrupt channels, to set up buffers, inform Sound4 about what sample rates are supported, what formats are supported. And there's also a new testing driver So this doesn't play sound, it's just used in the test suite. You can use it for testing patches. And each of those drivers, as I said earlier, they implement their own syscontrols. So USB driver has this syscontrols, HDA has this, and a few more. So again, after the talk, we can go through all these if you want, but there are too many to list now and explain. But this is just a rough overview. Sound driver talks with the hardware, talks with Sound 4. It's just an intermediate layer between hardware and the kernel, and then the user land. So how does someone write a device driver? Let's say you have a brand new card that you need to support. How do you support it? So first of all, you have to initialize, as with every driver, you initialize the internal resources. If it's a USB, you will do the PCI setup, you DMA, you'll set up any callouts you might want. Just normal driver initialization. Then you have to implement two interfaces that are provided by Sound, the Sound 4 module. I didn't explain them intentionally because I don't think there's really any reason. It's just, let's say, the communicating, one of the ways that Sound 4 communicates information with the driver. Again, after the talk, we can see those, what they do exactly. But think of it just a communication layer, a generic communication layer. So then you have to create a primary, as in hardware channels. If you remember, I showed here a bunch of stuff. So,
Can I just ask you a question?
yes, you can.
I'm getting a little bit confused.
I know.
I have background in audio. When you talk about channel, are you talking about a stream, or is it one channel, which can be like in a mixing board, there's one channel, one mic. So there's no question of a channel being mono or stereo. The stereo consists of two channels.
Yes. So I think I explained this before. So these channels that I'm talking about are not to be confused with the channels your sound card uses. So if your sound card has its own, let's say, 5.1 channels, right? That's in the sound card. But when I refer to channels, I refer to just the stream, yes.
Okay.
And then we do...
Maybe there's a terminology thing even in the naming, because a channel is very specific in audio.
Yeah.
It means mono.
So it does function like an actual channel. Like you just give it audio, it does the processing and everything, but it's just the software part of it. It's not...
And just another point, when you talk about channel matrix, that again has a very specific
This is exactly what it means.
implication, which is not surround sound. Channel matrix means multi-source, multi-output. That's what a channel matrix
I know, I
is.
just gave it as an example, like that
Okay.
we convert streams to stereo to 5.1 using this matrixing.
No, that's why I'm saying is that's not what a channel matrix is. A channel matrix would be you have a turntable, an MP3 player, a VHS tape player, and you want to send it to your bathroom, your kitchen. That's a matrix.
Right.
It's not what,
So maybe there's a terminology problem because we call it matrix, channel matrixing inside. So yeah, so I was saying, the driver creates the hardware channels. Again, the software streams for taking bytes from userland and bytes from userland to the kernel and to the sound card. So we create those channels, and these reflect, let's say, the hardware channels. Let's say if your device supports playback and recording, we'll make one playback channel, one recording channel. And so all the playback stream will go through here, and then to the sound card, and then the sound card will do its own thing and route it where it should be routed. So where are we? So we create the channels with this function. Then we register to Sound 4, just two functions. And we also create the mixer, and that's it. Well, then of course you have to implement those. You have to implement those interfaces, for example, the channels, how to set up buffers, how to destroy the buffers, keep track of the pointers. But that's not, I'm just giving a high-level overview here. But you can look at the code for the dummy driver to see just a bare-bones driver, how it should work. That's it. But it doesn't attach to any USB PCI, so yeah, you'll miss the actual USB parts, for example. But if you want to see just how can I get my driver to connect to Sound4 and actually have bytes from userland to the kernel, you can just look at this and that's fine. So hardware, actually I'm not going to talk about hardware because this is not a hardware talk. So once all this is done, samples go to the sound card and then microphone, as you said, speakers, turntables, mixers, all sorts of things. So there's no reason to talk about those, obviously. So some new improvements. Better laptop support, meaning you all know that some laptops, they have non-standard configurations and you might plug your headphones and not get sound out of them. So I'm trying to work on this. So I get reports all the time, oh, this laptop doesn't work, oh, I bought this new laptop, I connected headphones, and it doesn't work again, I'm going to switch to Linux. Yes, yes. That's actually very common theme every time. I know Alexander is here, and he's heard more complaints about laptops than me. And I have a patch that tries to address this issue in a more automatic way. I'm not going to discuss it right now. You can go to the review and yeah, leave your opinion. So I've made also some new tools. S&D control, I already showed examples before. If you use S&D stat, the character device, it's this, but in a more easy way to use. Plus, you can also configure things. So it's a combination, let's say, with the sys controls and the sound card and the sound stat device. So you can say sample rates, you can set sample rates formats, see how many channels you have, see what device is connected, feed the processing chains, all that stuff, just in an easier way. Also, MIDI dump, that's a bit unrelated, but it's also sound related, I guess. It's just a utility that you can connect your MIDI to, and you run it, and it just outputs whatever you press on your MIDI controller. I just made it to confirm that MIDI works. Like, does the driver, for example, recognize the notes correctly? Does it recognize velocity correctly? So you can connect it, run MIDI dump, give it the character device for your MIDI, and just press notes and it will show which note you pressed, velocity, and everything. Also, hot unplug is supported. I know for many years people complain that I have a USB card and I cannot turn off my computer, or my USB bus just hangs because I play sound and I try to disconnect my card. Now this works. So if you have a USB card and you just unplug it, it will work fine, no problems. Bug fixes and new bugs, of course. Cleanups, refactors, lots of them, which is the reason why there are so many new bugs sometimes. Tests, I've written some tests for the test suite. The kernel module had no tests before. I've written some simple ones for now. Also, floating point format support is now possible. I know, I know the wine port, for example, could not work. Some parts of it could not work because we didn't have floating point support in the sound. Now we have, but it's really just, we just take floats. Let's say if you want to play floating format to your sound card, it just, sound just takes the floating point samples and converts them to 32 signed samples. That's it. And it does the opposite if you want to record float. So you don't really record float, you just, it's like a translation layer. Yes. Maybe in the future we'll have actual floating point support, like send actual floating point samples to the sound card. But I don't think, does any of you use a card that actually works with floating points? And not, no, I mean internally works with floating points. Yes? And okay, so maybe we'll look.
That's not on FreeBSD, unfortunately.
Yeah, see, so I'm gonna switch to Linux as well. So yeah, so we could look into implementing support, actual proper float support. For now, I just implemented a very bare bones one so that ports can work. Also, since Hans Peter is no longer with us, I took over development of his program Virtual OSS and more stuff that I don't think is really notable. So I said if I have time, do I have time? Okay, So, FreeBSD for music. Why would anyone want to do this even? I mean, supposing you produce music, why would you do this on FreeBSD? Yes, he has turntables and runs FreeBSD. And so I would say the best reason you would do this for is because our sound system is just very fast and solid, and also very, you can configure it a lot. As I said, you can disable virtual channels and you get even lower latency. It's easy to work with, I think. Maybe it's a bit cryptic yet because of lack of utilities. So maybe to a user who just came to FreeBSD, it's not so obvious how do I do all this stuff. But I think with time it could be a very good option for sound production. And also, we have lots of new ports for plugins. LV2 is just, if you do music on Windows, you've heard of VSTs, for example. Yeah, LV2 is the open source equivalent of that. So there is a guy, I don't remember his name, but he's churning out new ports all the time with LV2 plugins. We can even do, if you play guitar, we can even do neural modeling. Does any of you know what this is or doesn't know what this is? Yeah, okay, so for guitar, even for a guitar player like me, it's great. I can already do most of the things I would like to do. I know if you make very complicated music, maybe it still lacks many of the features, but I think even if you use VSTs and you really need to use your Windows VSTs, I think there is a way to use VSTs on Linux and in general, convert VSTs to LV2. I think there is a possibility to do that. So I would say try it out. If you produce sound, music, you do podcasts, whatever, try FreeBSD. Maybe it's good. So do I even have next slides? I would like to thank Ed for usually the laptop parts. He's very helpful. Florian, he's not here, but he's a maintainer of Ardour port and Jack. He's very solid on sound. Goran Mekic is actually the one who inspired me to work on this. And he's also a FreeBSD musician, does metal, even goes to concerts and has a rack that uses FreeBSD live. So it's a very interesting. And that's it. Thank you. I hope I didn't confuse you all. Yes. I'll wait for the microphone. Yes.
This is great, Christos. It's my first exposure, but I'm going to ask you to just rewind a little bit. You put some emphasis on latency. The other half of it, so latency is like translation. You say something and it delays. But the other half is jitter, which is like a heart arrhythmia.
Yes.
Where it's inconsistent. So is that part of this work, or is there acknowledgement? Sorry, just the other part is you talked about test suites, and that may be something. Testing latency and jitter might be a worthwhile thing in the test.
So, yes, jitter, I think we do some. Actually, I'm not sure, so I might be wrong on this. I think we do some, corrections and stuff, but I think that's mostly the userlands thing to do. Am I right? Alexander, do you think that's the case?
Jitter is mostly hardware thing.
Well,
Jitter, in this case, more depends on hardware, since all the sound system, as was mentioned, plays in context of or synchronized by the sound card interrupts. When you are playing back something, its sound card generates interrupts according to the rate of data it receives. So all the conversions done by kernel, they are practically synchronized by the hardware playing hardware driver. I guess there could be some artifacts if you try to play from different sound devices with different synchronization rhythms, which are not synchronous, but those very special cases, I guess.
would it not be related to the driver itself, or if you're doing all of this virtualized process? A long time ago, a sound engineer told me, remember that sound is analog. We can play all we want in the digital world. What our ear hears is analog. So that's your ultimate standard. So everything that degrades along that path, along the digital path, is worthy of concern for fidelity.
So yes, sound does take care of this to some extent, but it's also the applications that need. For example, if you use a sound server, it will take care of it. But it's also hardware, as Alexander said. So the other question was, sorry, there was one more question you
Just
asked.
to add, there could be different implementation. For example, would we generate sound out of nothing based on sound on some third-party timer interrupts? There could be some fluctuation based on scheduling and everything. But here we practically have playback device which generates our fixed rate of 44,100 samples divided by rate divided by buffer size, which means we receive interrupt with fixed rate from hardware. And the only thing that we can do about is that can be counted as kind of jitter, but it has different, much worse effect, is that if we try to go for such a low latency that kernel cannot keep up, system cannot keep up with interrupt rate, and then we start skipping samples, not even samples, but skipping buffers. And it's much worse than jitter when it slightly fluctuates frequency, but we completely lost buffers and sound turns into garbage. So it's a question of latency, it's a question of sufficient buffering. We can shrink them as much as we can based on real-time priority, based on software optimizations and other things. But at some point, we just increase chance to lose, interrupt, and mess up everything. It should be just careful balance between those two. As soon as we keep within a range, all the jitter after that is question of hardware, how well it's synchronized.
Exactly, yeah.
And maybe just your test suite can
The test suite.
think about adding some of these, how much of that degradation is happening in the process.
Yeah. Yeah, it's still quite bare bones. So the test suite, it's just there to serve as a framework. If you want to write tests, you can follow. Yeah, so you had a question, I think.
Yeah, of late, hardware that I've come into possession with is at 48,000, and it's USB, and it's detected as hardware, and it even detects the 48,000, but the sound that comes out of it is like random, garbled, not even just sped up or anything.
So it could be that your settings. So as I said, you can set what the sound module will resample to. So if your card needs, let's say, 48,000, as you said, but you chose to resample at 44,000, maybe then there's a problem. Like maybe it's a problem with configuration. It's not really a problem with a card.
Well, in this case, for instance, it's a headset. You kind of expect it just to work, type of thing.
Yeah, I don't know. We'll have to look into this. I cannot debug it right now. So other questions? There. Too far.
Yeah, so maybe similar question. What's kind of the hardware that you can expect to work out of the box? What's the hardware support?
Well, all of them.
All of them?
I mean, USB works. I know you said you have a problem, but usually works fine.
Okay.
So the main cards that people use are PCI and USB ones. PCI usually being the internal one. It works, but sometimes you need to do some. I think at this point probably we've covered most of the laptops that need manual configuration. So I guess everything should work fine. I guess.
So if you plug like, I don't know, like a Focusrite or something like that.
I have a
you should
Focusrite there.
Should just expect it to work. Okay.
It works.
cool.
It works fine. Yeah, it
Nice.
works.
Pretty much any USB class compliant you can expect to work.
I find the USB ones to be the most solid ones.
What about older things like FireWire? Because there's a lot of hardware out there that is really good in terms of like DSPs and like
So-
chat, capability, but
So
the
we-
software has kind of like bit rotted in the world. It would be nice
So-
to save it.
I would say this, because I don't own any of these cards, I cannot really work on those drivers. However, I know we have many of them. There are many drivers that we have especially PCI ones, that work with all sorts of old cards and obscure hardware. So yes, I guess they should work, but I've never used them, so I cannot really give you any opinion on that. If someone else has used drivers other than the USB and the HDA one, maybe they can, yeah, answer this question. So any other? Yes? Sorry, are you tired of seeing Giorgio all the time?
So I have a USB device that works, and it seems to have different hardware profiles, and it seems to default to 2 channels in, 2 channels out, although it is capable of 14 in, 14 out.
Yeah.
And I wonder what's the mechanism to switch to one of these other profiles?
So you can use the virtual channel settings, like use the format and how many channels you want, or even better, you can use virtual OSS, the sound server, and it does multiplexing. You can use as many channels, you can map them to however you want. It's a bit complicated to use right now. I think if any of you has used virtual OSS, it's a bit cryptic to use, but it is possible. So we can look into this if you want.
I'm not sure we're talking about the same thing, because when it's in default mode, I cannot request more than 2 by 2.
Yes, that's the default, stereo. But you said you also have 14 channels and you want to use those, right?
Yeah, but it's really, when you use USB conf,
Yes.
you see this different profile, but I don't think I can switch to it. I cannot just request playback with like 8 channels.
Yeah, that's what I said. You can use virtual OSS to do that. And also,
Okay.
yeah, you can use it, definitely. That's the reason it exists, I think. The initial reason Hans Peter created it. So you can use devices with multiple channels and make them work properly. But I will have to look into this. I don't want to give a wrong reply and
I have
leave
the
this reply
PCI conf
forever.
dumped right here, so
Yeah.
anyway, thanks.
No problem. Ed?
There may be, there may be some device-specific tool or utility or something to configure it. I mean, I have a 18-channel Behringer mixer that it has a web-based control you can do on it, and it has an option for 2 in, 2 out, or 18
Yeah,
18,
okay.
and it's like
Yeah.
it's completely out of the scope of the USB port. It's just you configure it. So I mean, depending on the specific device, there may be something similar.
Sure.
As a musician yourself, which DAW do you prefer to use on FreeBSD?
Ardour.
Excellent, cool.
Dot. That's it, period. That's it.
Instantaneous answer.
Yes. It's very good. I mean, I would say it's even better than most of the Windows ones. I don't know. I think it's quite good. Very powerful.
What's that name again?
Ardour. Ardour. Next, or that's it?
I think I have 2 questions.
Yes.
One on support. I know you said you haven't necessarily used it, but do you know if there exists drivers for AVB cards? AVB, which is audio over Ethernet.
No, it doesn't exist. I know for a fact it doesn't exist.
Okay.
But because I thought there was no demand for it. So is there demand for this?
Is there what, sorry?
Is there demand for this?
I would use it.
Okay, so I see 2 nodding heads. 3. Okay, so we can look into this then.
And the second question.
I actually have it in my to-do list. But it's just at the very bottom of it. So now we'll go up the stack.
Okay. The second question I had is I encountered on Mastodon a whole thread about doing audio on the Apple M-based laptops.
Yes.
And how to get good sound out of those laptops, you need to do a lot of actual processing. You can't just send out a raw stream, and you have to do a lot of processing. I'm not sure if it's just EQing or other kind of processing to actually drive the speakers properly to get good sound. Do we have any of that in this vicinity, or is that something that hasn't been
I
thought
actually
about
am
yet?
so unplugged from Mastodon that I have no idea this existed. But I saw Ed also did yes, it is an issue. So please let me know, or send me an email. Let me know. Send me the thread maybe, so that I can look into it, because I've never heard of it.
Sure.
Thank you.
AVB? It's part of 802.1.
So, any other questions? You have 3 seconds. No, no questions. So that's it. Thank you very much. I hope I didn't confuse you a lot.
should run away now.
Is there nothing more interesting?
Isn't Michael Dexter doing his how to submit a bug report talk at the same time? I have opinions on how you submit bug reports. I'm just waiting for the go-ahead from our video people. That looks like a thumbs up, so there we go. Welcome to a packet journey through PF. Let's start with the obligatory who am I? Who am I again? Oh yes, I'm Christoph, KP at FreeBSD.org. I've been a committer and basically the PF in FreeBSD maintainer since 2015. So everything that broke with it in the last decade is my fault. That all happens because I looked at what PF did at the time with IPv6 fragmentation, and I had the brilliant idea that, you know, I think I can make this better. And I still haven't escaped. Since early 21, I've been basically maintaining PF full-time for PF Sense, thanks to Netgate. I failed to bring the hat, otherwise I would have put the hat on. The actual introduction, where does this talk come from? It is shamelessly stolen from Alexander Bloom's talk, A Packet's Journey Through the OpenBSD Network Stack. He presented this at EuroBSD, YouTube link there. I'll give you all 2 seconds to write that down. It's a very good talk. It gives a good overview of how packets transit the OpenBSD network stack that turns out to mostly apply to FreeBSD as well. It is very nice to have that context for this talk. I found myself unable to squeeze a 40-minute talk in front of my 40-minute talk in a 40-minute slot. So we're just going to spend like 2 or 3 minutes looking at the FreeBSD network stack and where the firewall fits into that. Quick disclaimer about what we're going to be talking about. This is based on FreeBSD main as of today-ish, as of a couple of months ago. Some of the things I'll say here don't apply to stable 14 or stable 13. The concepts are broadly the same, but there's been a fair amount of refactoring, which is a polite way of saying code blatantly stolen from OpenBSD, but they haven't noticed yet that we stole it, so it's fine. Don't tell them. Anyway, the network stack. What happens? Packets come in, device driver does magic. Let's not get into what they all do. Hand the packet over to Ethernet input. This, of course, assumes that it's an Ethernet packet, but the entire world is Ethernet. We could just forget that anything else exists. The Ether input function will demultiplex this because it could be an IPv4 packet, an IPv6 packet, it could be ARP, it could be spanning tree, it could be any number of things. Assuming that it's IP, it'll hand this to the IP input function, and then depending on what's contained within or where it needs to go, it'll forward the traffic or it'll terminate it locally in TCP and hand it over to the socket layer where hopefully an application will look at it and do something useful. The same thing happens on the way out, just in the reverse order. One of the things to remember here is that the order of operations for input packets versus output packets is inverted, of course. On an input packet, you handle Ethernet first, IP second. On an output packet, it's IP first, Ethernet second. So where does the firewall fit in? Well, right there. In FreeBSD, we have, because we love our users very much, we give them the choice of 3 different firewalls. So what we have is an abstraction layer in the network stack that says this is where we need to call into the firewall. That's called pfill or netpfill. And then depending on which firewall you have loaded, it'll dispatch to the correct firewall. You can actually set multiple firewalls. You're allowed, there's no law against this. Just know that my support policy for that situation is that I will point and laugh at you. There are people who do this. It sort of works for them. There are any number of things that will go wrong with this, hence the support policy. Just don't do it. Just pick a firewall and stick with it. IPFW is very nice. slight simplification here is that I've only listed the pfill hooks in the IP layer here. There are also pfill hooks on the Ethernet layer, so you can do layer 2 filtering. IPFW does a great job of this. PF does a very basic job of this. We'll get to that later. Key concept for PF. PF is a stateful firewall, and the stateful bit really does matter. There is, of course, an exception. The layer 2 bits in PF are stateless, where we look at every packet individually without any further context. PF is stateful even for stateless protocols like UDP, because it turns out that in practice, while UDP is, stateless, for the vast majority of UDP traffic, DNS, you're going to see request-response. And PF will treat the response as being part of the same connection as the request. This makes writing your firewall rules a lot simpler. This means that you can write stricter rules. It is the 21st century. Do not accept stateless firewalls anymore. So we've got states. We also have rules. The rules are what policy are we going to apply to the packet or connection. Interesting thing, well, the important thing to remember here with PF is we process rules let me rephrase that. We always look for a state before we process rules. So if a state has been created for a connection, it doesn't matter what you do to your rule set, that connection will stay alive. We'll come back to that, I'm sure. Very high level overview. What happens, remember the network overview, packet comes in, it hits PF, it hits pfill, it gets handed off to PF. We enter PF in the PF test function. Strictly speaking, I've just lied to you. We actually enter PF check in or PF check 6 in, but those functions really don't do anything. The fun starts in PF test. PF test tests a packet. What does it do first? It sets up a packet descriptor, PF setup pdesk. This packet descriptor contains a bunch of context information for the packet. It helps us to avoid parsing and reparsing the packet. It remembers things like what interface did this packet come in on, where's the layer 3 header, where's the layer 4 header, what's the source address, what's the destination address, what was the source address before we applied the NAT transformation, stuff like that. So that's where we do most of the packet parsing. We also do packet normalization. That's PF speak for let's make this packet look the way we want it to look. The biggest operation there is reassembly, where if we have a fragmented packet, we wait until we have all of the fragments, we turn it back into the fragment it was, into the packet it was before fragmentation so that we can look at the full packet. This is important because you want to be able to filter based on the actual packet. And if you're fragmenting a packet, especially if you're a malicious user, you might fragment it in the middle of the TCP header, at which point we don't know what TCP port this packet belongs to, and you get to make a very difficult decision between, do I drop this packet and break fragmented packets for everyone, or do I accept the packet and then implicitly accept that anyone can bypass the firewall by just fragmenting their packets in a strategic location? Hence my motivation to do the IPv6 reassembly work. So we take fragments, we reassemble them, and then we continue processing on the fully reassembled packet. We'll come back to that in a little bit because that is relatively trivial for IPv4. There's some gotchas in IPv6. Anyway, we've reassembled the packet, so we have a nice big packet to look at, or it was not a fragmented packet in the first place. The next step is we PF test state, and then it's protocol specific. That has been unified a little bit. I believe these days it's PF test state or PF test state ICMP, because ICMP is very special. What does this do? It goes and looks for a state. Have we seen packets belonging to this connection before? If we've seen this before, if we find the state, we process the packet according to whatever we did, whatever we have stored in the state. So the same thing that we've done for other packets. If we don't find the state, that means this is a new connection, and presumably this is the first UDP packet for this connection, or it's a TCP SYN. We're going to do PF test rules, or test rule, which is we're going to process the rules and we're going to figure out what do we want to do in this particular case. Either way, either we found the state or we've processed the rules. We need to handle output. There are a number of things that we can do to packets. We can pass them unmolested and say, this is a good packet, I approve of this packet, it can go. We can throw it away. We can reject it, which is we throw the packet away, but we generate an ICMP error or a TCP reset so that the other side knows that this connection failed. We can route to, which is policy routing, which is where PF says, I know the routing table says the packet needs to go that way, but actually we're going to send it that way. This is in PFSense specifically used to do multi-WAN setups where you have multiple uplinks and then you want to bind your connections to a specific uplink, but you only have the one default route, of course. Finally, and this one is relatively new, is AF2, which is address family translation, which is NAT64. So that's new in PF, well, new in FreeBSD PF. We took the OpenBSD code and ported it into FreeBSD. Along the way, found a very amusing bug that also affected OpenBSD. Happily has been fixed since. So in FreeBSD 15, you'll be able to do NAT64. Or you can just install PFSense. Latest release has NAT64. I promised I'd come back to IPv6, because IPv6 fragmentation is special. I'm sure some people here think, because it's a common misconception, that there is no fragmentation in IPv6. This is not strictly true. There is a difference in fragmentation between v4 and v6. You remember in v4, if a packet is too big, any intermediate router along the path to the destination can go, oh, this packet doesn't fit down my outbound interface, I'm going to fragment it and send the fragments onwards. v6 is different. In v6, the intermediate routers cannot fragment the packet. So if they get a packet that won't fit down the next hop, they generate an ICMP6 error, send that back to the sending host that, hey, your packet doesn't fit, try again. So you end up doing a path MTU discovery, and it is your sending host that will fragment the packets. It is only the receiving host that is supposed to reassemble them. But because of the discussion we've had, you really want to reassemble your packets to do proper filtering. We do reassemble them in PF, but then we're left with a big packet that potentially won't fit out the interface that we're trying to send it out. But also, if we reassemble and send it out that way, we're going to break the path MTU discovery. So what we do while we're reassembling an IPv6 packet is we remember the size of the largest fragment we saw, and then we reassemble based on that size. So there's a little gotcha there in the sense that if you have an interestingly fragmented packet, so your packet, you send 20 bytes, 20 bytes, 1,000 bytes, 20 bytes, 20 bytes. The way the packet looks, or the packets look on the way out, is it's going to be 1,000 bytes and then whatever's left over. Now That's theoretical, because in practice, all sane code that fragments packets is going to fill the MTU, and then only the last packet will be whatever's left over. So if you do that, it'll work just fine. If you don't do that, you might see strange things. So as we output the IPv6 packet, we look at the information that's associated with it that says, oh, we've reassembled this. This is the size we need to refragment to. We refragment the packet. We generate a whole bunch of new packets and output those. Second gotcha with that is that PF will actually call IP6 output or IP6 forward directly. So usually, if we go back to this, usually you will catch the packet here in the pfill hook. we'll gather them up, finally we'll reassemble, and the packet will continue its life through the network stack as a return from pfill. Rather for IPv6, when we're transmitting a refragmented packet, we're going to call IP6 forward or IP6 output directly. So the actual function flow is slightly different, and this is because the pfill hook understands the notion that it gets given a packet and it returns 0 or 1 packets. You can have no packet returned, we ate it, or we can have, here's your packet back, potentially modified. What it doesn't understand and what the calling functions don't understand is that you give 1 packet to pfill and it returns a whole chain of packets. So to bypass that problem, we end up calling IP6 output IP6 forward directly. There's a lot of context here. There are some implications to how this behaves. Remember that we test for state first. I've already mentioned it. It means that we only evaluate rules if no state is found. So if you change the rules, say that you had a pass all policy, we set up a whole bunch of connections, and then you apply new rules, you say block all of your existing connections will continue to function. Because the packet will come in, we'll do a state lookup, we'll find the existing state that says, yes, this packet is allowed, we'll apply that, and we'll just continue. We will never go look at the new block all rule. So if you want that behavior, you have to flush all of the existing states when you set new rules. Sometimes it's useful, but be aware that this is a thing. It can bite you, and I'm sure we've all been bitten by, here I've edited my rule set on this remote machine, I've applied them, and I can't connect to the machine anymore. I'm sure we've all done it, and if you haven't done it yet, you'll do it at some point. More implications of this. State lookup is incredibly important for PF performance, because for any given connection, we're only going to do rules evaluation for the first packet or maybe the first 2 packets. Everything after that is a state lookup and an output. So it is when you're benchmarking how many packets can I throw through this firewall per second, it's the state lookup that's important. So how does this work? And with this, again, a disclaimer, it is different on FreeBSD versus OpenBSD. On FreeBSD, we have a hash table. So we take the source and destination IP address, source and destination port, or for ICMP, type and code, the address family, and the protocol. And we hash this together, and we end up with a hash row, and we go and look in that row that is potentially a list of states. Do we find this state? So you can have multiple states in any given hash row. There are performance implications to this, of course. If you have many more states than you have hash rows, your lists on average will grow. And doing a linked list transition, of course, is a lot slower than doing a hash table lookup. So you always want your hash table size to be scaled somewhat reasonable given whatever state limit you want to implement. You're going to be okay if you have 2, 4, even 10 states in a row. It'll probably be okay. But if you have 1,000 times more states than you have rows, you're going to see your performance start to crater. There's a tunable for this, net.pf.states hash size, so you can't change that at runtime. You do need to reboot to apply it. If you set it too large, there are downsides. You're going to use more memory, but memory is cheap and I don't have to pay for your memory, so set that large enough. There are dtrace probe points that you can use to instrument how many states you have in any given row. That's the pf purge state row count probe point, and that gives you the row number and how many states it saw in that row. There's a cleanup process to delete expired states that will iterate through the hash table, and while it's doing this, it'll generate these probe entries. Another thing that is important for state limits is the way we implement this limit is we use a UMA zone and say you can never allocate more than X amount of items from this zone. That's fine and that works, but if you run close to the limit, you will end up with very, very slow allocations because UMA has per CPU buckets of memory that is ready to hand out. And as long as there is memory in your per CPU bucket, the allocation is very quick. But once you start to get close to the limit, your local bucket is going to be empty and you're going to have to talk to other cores, and it ends up being quite painful to actually hit the limit. Moving on, control plane. So this is how we configure PF. This is not particularly interesting in and of itself. It's just this is how PF talks to the kernel. And right now there are 3 ways to do it. We've got the old ioctl style, which is all that OpenBSD does. And that's a fine approach to do it. It's where you copy a structure from kernel, from user space into the kernel back and forth. And this works, and this is simple. And this is extremely painful if you change any of these structures. If you add a field, if you change the size of a field, all of a sudden user space and kernel space no longer agree, and you're in trouble. You can fix this by just telling user space, hey, recompile, and it'll be fine. The first attempt we had in FreeBSD to make this better is sticking NV lists. NV lists are name-value pairs, sticking those in the ioctl rather than a fixed structure, because then you can add fields without breaking compatibility between the kernel and user space. This is an improvement, but it is still a little bit annoying. The ioctl interface makes it really annoying to deal with the dynamic memory sizes that you need to make that work. And also NV lists don't perform particularly well. And this is fine for small commands, you know, add a rule, show me the list of rules, give me the status of PF, that's all fine. If you have bigger requests, like say, I want to export my PF state table that has 1 million entries, it is not fine. And it consumes all of the memory on your system, and it also takes forever. The third option is netlink. Yes, that netlink, the one you know from Linux. It's a socket that communicates user space to kernel space, or possibly kernel space to kernel space. It also has a type length value encoding, so it becomes easy to add fields to a request and it won't confuse the other side. It scales really well, so when I ported I didn't do the port. I'm blanking on the name. One of the Yandex people implemented netlink. And he also did the port to do the state export via netlink. And once we tweaked the user space a little bit to export 1 million states, instead of needing 4 gigabytes of memory, we needed 16 gigabytes of memory, and it was a little bit faster than the old ioctl style. So if you're a user, or if you are user space and you're trying to programmatically interact with PF, it's really annoying to have to deal with all 3 different methods. I would recommend strongly that you don't. There's a library, libpfcutl, that implements many functions, not all yet. This conversion is in progress, rather. But if you have an application that programmatically interacts with PF, please, please, please don't try to implement the ioctls or netlink yourself. Use the library. If you're missing functions, tell me and we'll implement them. I have an aspiration to convert everything to netlink and then to get rid of the old ioctl interface. That isn't done yet, but if you use libpfcutl, you don't have to worry about this. You just call a function and it'll do it for you and it'll be okay. So, you know, if you take nothing away from this talk, take this. If you're doing programmatic interaction with PF, use libpfcutl. Don't write your own ioctl implementation because it will break and I won't feel sorry for you. We're talking about a kernel system, so we just cannot escape talking about locking. There are a couple of different locks in play for PF. There is a rules lock, which protects the rule set. This is a read-write lock, or rather a read-mostly lock. That is to say, you can have any number of cores at the same time, take the read lock and process rules at the same time without interrupting other cores. It's only when you modify rules that you need to take a write lock and that you're going to stop traffic on all cores while this is going on. I say read mostly because we have two types of read-write locks in FreeBSD. There is the read-write lock and the read-mostly lock. And the only difference between the two is that the read-mostly lock is optimized for read workloads, so where you have many more read locks than write locks. And that turned out to be relevant. Babak Farouki did the conversion of our read-write lock into a read-mostly lock, and we got a 65% improvement in packets per second for a mostly trivial patch to convert a lock type. So that was really nice to have, but slightly embarrassing. It took us that long to notice. He was actually trying to fix a NAT bug that was completely unrelated to the locking. He just accidentally gave us a 65% improvement in throughput. So I wasn't particularly upset with him. Especially not because he later built a test case to demonstrate his NAT problem, which enabled us to actually fix the NAT problem as well. We also have a state lock. So when we do a state lookup, we lock the hash row, which is another reason why you don't want too many states sharing a row, because you have the potential for multiple cores at the same time trying to lock states in the same row, and then you've got contention, and that's the enemy of your throughput, of course. So we lock per hash row, as I said. Another reason to make sure your table is well dimensioned. The state lock is a little bit interesting because I've kept things simple when talking about states, but it is, of course, more complicated than this. Because your state is based on your source IP address and port and protocol, and it turns out those can change. You can do NAT, you can do network address translation, you can change. This means that the IP addresses in the packet can be different on one side of PF versus the other side of PF. So what we do is we have two different states, state keys in the state tables that point to the same state. But you need to lock both hash rows in the state table to safely manipulate them. And of course, having to deal with two locks means that you have the potential for a lock order issue. If you've got two cores at the same time trying to deal with the same state, and one of them locks the first row first, and the other one locks the second row first, and then tries to get the other lock, you've got a classic deadlock, and those are not good. They're terrible for throughput. Great for security, though. So the way we solve this is that if we have to lock two different rows, we always lock the numerically lower one first, and that guarantees that we take the locks in the same order on all cores. And if you've got two cores trying to deal with the same state, at least they will both try to lock the same row first. So one of them is going to win and be able to make progress. The other one is going to contend on the lock until the first one is done, but at least it'll eventually make progress as well. There's more locking to talk about. PF users may be aware of PF sync. That is where we synchronize state information to another host. This is strictly a failover feature. Do not confuse PF sync for a performance feature, because you will be sad. What this does is every time that we update a state, it will send these updates off to the other host, which will reconstruct the state table so that if your primary host goes down, the other host can take over and have all of the state information, which means you don't have to drop any existing connections and your users are happy. It also means you can do firewall upgrades without impacting traffic too much. You're always going to lose some packets, but it's fine. It's just network packets. The problem here used to be that we had the nice and shiny clever locking in PF to make it all very fast, and then we'd enter PF sync, and the first thing PF sync would do is would take a mutex. So it doesn't matter how good we were in PF to run across multiple cores. The moment you the moment you loaded the PF sync module, you were stuck with single core performance. This makes people sad. So a few years ago, actually I'm looking at the commit back in 2018, I did some work for Orange to make this better. So what we do now is we split the PF sync updates into different buckets. Essentially, we map a whole bunch of state hash rows onto a single bucket and lock that bucket, which means that other states that are hopefully going to map to other buckets can proceed while this is going on. We've seen performance improvements 30 to 100%. You can tweak the number of buckets. My experiment showed that if you've got twice as many buckets as you have CPU cores, you get most of your performance without making things too much more difficult. And that is live in all current FreeBSD versions. Because as I said, it was done in 2018. You still pay a little. There's still performance overhead to running PF sync, which is why I say that this is not a performance feature. Don't think that you can balance load between multiple PF firewalls and synchronize them with PF sync and get them to work faster. It's not going to work. It'll be slower. Another shiny feature is somewhat recently PF grew basic layer 2 filtering. As I've mentioned before, this is entirely stateless, but we can do things like, Ether, because it's an Ethernet rule, pass protocol 806, so allow warp packets. Allow all traffic from this MAC address and tag other packets, because these are quick rules, with the captive tag. The whole intent of this exercise was not to build a very capable layer 2 firewall, it was to enable captive portal features. So we're all familiar with the captive portal where you get to a hotel Wi-Fi and it's an open network, but you log on and they redirect you to a specific web page so you can give them money before they let you get to the internet. Or sometimes so they can give you a disclaimer before they let you. But anyway, we like to remember the MAC address of the host to do this, to say, okay, we've seen you before, you can log in and pass unmolested, but you need the MAC address, which we don't have in PF's layer 3 rules. So we do this in layer 2, we tag packets appropriately, you're allowed, you're not allowed, and then we can do the layer 3 actual complicated actions in there. Really mostly just want to point out that this exists. This is FreeBSD 15 only. Next one, SCTP, also an Orange project this. Those of you who don't know, think of SCTP as TCP, but with multiple flows embedded within it. It is the unholy love child of TCP and UDP. It supports multi-homing, which is why it's interesting for the firewall. Because you don't just get the one connection where you set up a connection where it's very similar to TCP. It might also contain additional data that says, oh, by the way, I have this and this and this other IP address, and you can also talk to me on those. So what PF does is it looks at all of those packets. They're called ASConf chunks in SCTP speak. And based on the IP addresses that we see in there, we will create additional states. So that if you've connected from IP address A to B, and host A has said, I also have IP address C, and host B has said, I also have IP address D, we go and create states not just from A to B, but also C to B, C to E. Anyway, I'm losing track of my letters here, but we create all of the possible combinations of connections so that when those hosts decide to start speaking to each other using their other IP addresses, they will just pass through and all will be well. This is also unique to FreeBSD PF. I am not currently aware of any other open source firewall that handles SCTP multi-homing, which is why I mention it. I feel vaguely proud of this one. It hurt to get it to work, but it does work. So that's very nice. One more thing to talk about is counters, because it turns out to also matter for performance. So counters are where we count things, where we count how many packets and how many bytes any given rule or state has matched, possibly even for interfaces. And we used to do this, you had a uint64 somewhere and you just increment that number anytime that you hit it. And it's not necessarily obvious, but it turns out that this is terrible for your caching performance, because you've got one core updating this and invalidating the cache line, and then another core tries to also update it, but you get memory accesses. Anytime that any core touches it, you have to do memory accesses, and it is slow. There is a counter framework, counter 9 in the kernel, that counts per CPU. So you keep a per core count of whatever you're trying to count, and it is only when user space asks for the total numbers that you go and look at every core and ask for their numbers, add them all up together, and you get your total. Advantage being performance. That's what these counters look like, or what they look like in the rules. That's all very nice. This is a relatively straightforward conversion to do. The biggest problem with it was that PF, coming from an OpenBSD side, tended to conflate the data structures, the structure definitions that it used for communication between user space and the kernel, and the data structures that it used internally to the kernel. Those were the same struct. So you can't change that struct in the kernel without affecting user space, which we don't want to do. So most of the work to convert this these counters to use the counter 9 was splitting up those structures, doing the conversion between structure type, and only then could you make the change inside the kernel. This was another nice big performance improvement, and I think this is the one that pushed us to the point where, again, the last numbers I saw were from Olivier, were a few years ago, but at that point, IPFW and PF were basically tied for performance, right? If I'm remembering correctly, IPFW was still marginally faster, but it was very, very close. One more thing I want to point out is there's a bunch of static probe points in PF. Some of these are potentially really useful. We've mentioned the PF purge state row count, which means that you can monitor how many states you have in any given hash row. So that can be interesting if you're trying to diagnose performance problems, for instance. There's a probe point for ioctl errors, which is really handy if you're not sure why your ioctl call is failing. It can return the error number and a line number. There's some debugging probe points for SCTP when we're adding or removing multi-homed entries. There's probe points for when you're doing Route 2, and those probe points, I assure you, are there because I keep having to fix bugs with Route 2, Reply 2, Dub 2. Those are extremely useful to me. They may or may not be useful to the regular or average user, but they exist. There are more. As is always the case with dtrace, honestly, to make the most out of them, you really need to be looking at the source code to see what we're actually probing. There is also no stability guarantee of these, of course. This is all very specific to the kernel internals, and that's... I don't want to paint myself into a corner saying, this is how we're going to do it and nothing else. So they may change. I think I've covered everything here, so if there are questions, please feel free now. Questions, comments, complaints? Yes, we've got one person up there. I was told I wasn't allowed to throw it at you, so... Sorry. There we go.
Did you say Netlink uses 4 times the memory than NVList when doing the memory states?
So Netlink uses its own type length value encoding. It's conceptually similar to NVList, but it is not the same encoding.
Please, what is the performance gap between Netlink and NVList?
So the performance gap is there are basically two different advantages of Netlink over the NVList. The first is memory use. From the kernel to user space, Netlink can start sending data immediately. But with NVLists, we had to build the entire reply and copy the entire reply to user space in one go. That's where the memory improvement comes from. There's an actual CPU time improvement as well, and that is just purely because the NVList internal data structures don't scale well to very large lists. And again, this isn't really a criticism of NVLists, it's just a fact of life with them. If you use them for what they're intended for, they work just fine. It's when you start to abuse them for, I would like to return 1 million states, that things break down. Yep.
Okay. I think we tried loading 50,000 rules with NVList, and it took about 60 seconds.
Yeah.
And so, relatively, how long do you think Netlink would take? Like around 50,000
I would expect Netlink to do significantly better. I can't really give you numbers there. What I can do after the talk is I can point you at my commit where I have some numbers for the state export. There's some timing information there. I don't know off the top of my head what the timing was. But also, 50,000 is quite a long way from 1 million. Of course, 50,000 is a lot for rules, but it is not a lot for states. Anyone else?
All right, so we got 4 questions from IRC. I guess we'll just let you answer as they come
Sure.
along. But first question from IRC, is the state hash table protected against hash collision attacks?
Yes, that is a good point. Yes, it is. At startup, PF will generate a random seed, and that seed gets stored into the hash table. So you would need to know that random seed to be able to deliberately provoke hash collisions.
Okay. All right, actually, we just got another question, so there's 4 more questions. Let's see here. Is there any documentation on writing Netlink generic services inside the FreeBSD kernel?
I'm not aware of any documentation. Best I can say is go look at the existing code. I don't think any specific documentation got written for that. Someone should do this. See one of our documentation people desperately diving for cover.
Okay. Does PF on FreeBSD support tables of MAC addresses for layer 2 filtering?
No. It does not currently support tables for MAC address filtering.
Okay. How many SCTP endpoint-to-endpoint combinations does PF track? Is this vulnerable to O(n)² state exhaustion attacks?
That is a very good point. I don't think we've actively considered this. So I think right now it is unlimited, and you could potentially exploit this.
Okay. And I think that's it so far. Are there any dtrace probe points users could use instead of PF log for debugging rule sets?
I was going to say there are probe points in the PF test rule function, but I'm not actually sure if I wound up committing those probe points or not. I'd have to go look at the code to tell you.
All right, and then there's that one last comment. Someone, trademark, should do this. Mwahahaha.
Yes. Tell this person I will find them. Going once. Going twice. As far as I can tell, we've all survived this. I think that's a wonderful result.
All right. Okay. Hello, hello. Welcome to my talk. This is Pork. It's not what you expect. This is kind of a multi-dimensional title because one, you didn't really expect me to pronounce it like that. And two, it tells you kind of what the software is if you have any familiarity with expect. So this is a software project I've been working on in my spare time to kind of enable testing for TTY functionality on FreeBSD. Instead of Tickle, it's scripted with Lua. So it's a little bit more friendly and a little bit more consistent with what we write in other parts of the base system. So a little bit about me. I'm currently the FreeBSD engineering manager at Clara. I've been a FreeBSD source committer since 2017. As for this talk specifically, some of the relevant work that I've done, Warner Losh had integrated the Lua loader in 2018, which is where I generally learned Lua to start with. In the next year, I did a lot of work with that, and we got it enabled in time for 12.0. I then pushed for Flua the next year, and we got that added to the build so that we can start rewriting stuff in base in Lua. Then we've since rewritten just a couple of, kind of build tool type stuff, the tool that we use to generate syscall tables, and recently landed a remake for our makeman.sh, which we use to generate source.conf. The main advantage was being able to add parallelization. We did a lot of fork and exec stuff there, and it generally improved it pretty well from, I think on the Mount Snow system I did, it came down from something like 2 minutes to 30 seconds. So that was kind of a significant improvement. I've done other things in FreeBSD, but I kind of work a little bit of everywhere, so it's nothing really significant to put on this kind of slide at least. Otherwise, I'm not good at pronouncing things and I'm not good at producing diagrams, so I apologize and we'll hopefully just get through this together. So today we're going to talk about the motivation, why I bothered writing this in the first place, and why I didn't really think expect was good enough for what I wanted to do. We'll talk a bit about the design and some of the choices that were made to enable the kind of testing I needed to do. And we'll talk about some other kinds of features that I built into it that are also generally kind of useful. And also we'll show some examples. I wanted to do a demo, but the demos aren't very interesting because you just run the script and then get no output, so that it's kind of not very fun to watch. So first, motivation, just diving into the background a little bit. Pretty much every Unixy, POSIX system, you're going to find some kind of pseudo-terminal driver. And this helps us overcome one of the challenges that we'll talk about in the next slide. And we generally, the control side is software driven to mimic a user so that we don't need to actually physically reproduce these reports and make sure that they don't regress. So terminal canonicalization as well. So when you have generally a program trying to read, will only read one line at a time rather than reading every single byte. And so the kernel generally does the line splitting and then only returns when we have a whole line blocking in the process. And then the EUF character, which terminates the line or sends an EUF to the program. So if you have, for instance, cat, send the EUF character, then gone. And specifically, the motivation was a single bug we had there and making sure that we had that tested so that someone else doesn't come along and break it again later. That's pretty much it there. So what I wanted was adding tests for the TTY layer. I can fix the bugs that we have, but there's no way to assure that they're not coming back. Nobody is testing much of this stuff on a consistent basis. And I don't really work on TTY stuff all that much, so chances are someone like Christoph could just come along and break it later for us, and we would just never know. And that includes things like this first one here where they had a 6-byte buffer, and you type in exactly 6 characters and then hit the EUF key, and then it would read the six characters and then terminate because we didn't eat the end of line that should have been consumed by the line. And that was generally the motivation for this. I also decided when I was kind of looking at what I wanted to write that it'd be useful to be able to do some basic program orchestration, which is also how the name kind of came about. I'm not very creative, so just abbreviation for orchestration seemed like the way to go. And then somewhere in the middle of this, there was a Rust library of the same name that was released, so it ended up getting renamed to Pork, which was program orchestration, which is kind of why I pronounce it a little bit differently. And then I also saw some potential for other interactive program testing, which we have some plans already to do this kind of thing, but we haven't widely deployed it yet. So if you're not that familiar with Expect, in their own words, it is programmed dialogue with interactive programs. It's scripted with Tickle, which I'm not really fond of. This isn't a thing that I use more than like once a year, so I generally don't want to have to keep referring to manual every time that I need to write it. And Lua, I use much more frequently, and I find it a little bit more friendly in general. So that was obviously a pretty big motivation. Otherwise, it's fairly complex. There's a lot of use cases that Expect tries to cover that I didn't really want to care about. And it just didn't really feel like a good fit for what I needed, because I needed to be able to control some other aspects of the TTY. I needed to be able to stall it a little bit while I prepare input for the program to read. And it's also public domain, which kind of poses its own challenges sometimes. So it was much easier to just write my own thing that didn't really have any of these problems. And some of the challenges when you're trying to do some of the TTY testing I wanted to do is we didn't really want to race the program trying to read. I wanted to be able to hold it until I was ready to, for the program to actually try to use the TTY. Some of the test cases we need to write are kind of tedious to generate. Things like, okay, we need to make sure that we need to try to flood the input queue to try to see what it does when it has to queue up more than that. So that's also not very fun to do in some languages. And I wanted an easy way to send control sequences without thinking about it. I wanted, when you read this, I want you to see, okay, I have this char C, I know you're sending a control C. That's just, it's not really a big deal, but it's just a minor readability thing that's kind of important to me. And I wanted to be able to do some of the kinds of things that STTY does so that I can, for instance, disable canonicalization and the other kinds of things that I might want to do. So talking about the design a little bit, it's scripted with Lua, 5.3 and up, mainly because I used some bit operations and I didn't really want to deal with compatibility for earlier than that. FreeBSD's Flua is 5.4, so that's kind of convenient. I don't really need to care about earlier than that, but 5.3 is easy enough to do. It has both a scripted mode and a direct execution mode, which is generally just library usage. It's pretty portable. I tested in CI on FreeBSD, macOS, and Linux. I'd like a solution to do the same for NetBSD and OpenBSD, but right now I settle for just testing it before I cut a release, just to make sure that it didn't regress. Normally I don't really have any problems with that. It just kind of works. The test suite does need at least NetBSD 10 because I needed the RealPath program. I didn't really feel like working around that. And OpenBSD and NetBSD both failed one minor test because they're missing the capital S for env to do word splitting, because the file name needs to go to the -farg instead of the first non-option argument. So the kind of process flow that this generally has, so you spawn an application, and when you spawn it, we don't actually execute it immediately. It sits in process hold, which we'll talk a little bit more about in a minute. And then from the user perspective, you then go into a write match cycle until you are done with your test, and then you send it to end of file and you close it out. Kind of deeper look into that. So that process hold is sitting, the process is sitting post-fork pre-exec, and it just kind of waits so that we can send it IPC. This is where we can configure different things about the TTY, or we can configure different signal handling. And only some of that really needs to be done at this point. This is also where we may buffer up input so that we can make sure that it's all there before the program has a chance to try to read it. From there, the program gets released, either implicitly or explicitly. If you try to do something that would otherwise block if the program's not running, then it'll just go ahead and release it because that's clearly what you meant to do. And then it goes into the run state, which lines up with the previous write match cycle there. Until you close it, ideally, it just closes cleanly, no problem. If not, we'll send it to SIGTERM. Previously, that was a SIGINT, but I decided that was kind of a dumb idea, and I don't know why I did that in the first place. And then if it still hasn't died after 5 seconds, we'll send it to SIGKILL just to make sure that it's actually gone. When it's in the release or pre-release state, you can configure different things about it. The only one that you actually have to configure at that time are signal mask and signals that are ignored or caught, just because we can't do that without more magic once it's no longer in our control. Otherwise, you can configure different timeouts, write speeds, which is also kind of borrowed from expect. You can configure most term IO settings. So any C flag, I flag, L flag, or O flag you can set, as well as control characters. You can also change the window size, which is maybe a little bit weird, but at Clara we did I don't remember if we had implemented it or improved it, SIG winch handling in script. So I wanted to be able to test what happens if we resize the terminal as we're writing to it. And so that kind of motivated that one. It's fairly easy to do once we already had other term IO stuff we were working on. So it seemed like a reasonable thing to do. The scripted mode, these are org scripts. It's a very limited environment. So it reads the script, everything you can execute. It's generally in a limited sandbox, and everything will more or less create an action that it enqueues for later. You can still generally write arbitrary Lua, and it's still Lua, but it's a little more complicated. You have to think about exactly what's executing right now and what's going to execute after everything starts running. There's some things I've done to be able to paper over some of the differences so that it's really not that bad. In scripted mode, you get one process at a time. So you spawn the process, you can operate on it. If you try to spawn another one, we're going to kill the first one. We don't need that kind of complication in our life. If you feel like you need multiple processes, that's kind of what the lib mode is for. And we also kill it when the script ends, so that we're not just leaking, things like that. As far as actions go, we have a number of things that you can do in scripted mode. We won't really talk about all of these, but like we had said before, you can configure the write delay. We have several options for configuring signal. Signal masks, or what's ignored, what's caught. You can send signals to the process once it's running. This is useful for things like Unix conformance testing or testing specified behavior, because you may need to get to a prompt and then send it SIGINT and try to observe how it responds a little bit. It can operate in the environment. There's also an option to pipe in from another program, which is kind of neat if you need to, for instance, read secrets from somewhere else. For instance, maybe a password prompt. That's a good option for that if you need to avoid putting any secrets into your script. And we'll talk about some of these in a little more depth. There's also, by default, when you're doing matches, it uses Lua expressions, which aren't necessarily the most intuitive. So there are options to switch it to other matchers. You can either just do plain text matching, or you can even use POSIX EREs, which are a little more natural feeling, in my opinion. So match and one are the basic primitives that you're working with. So match is the basic pattern match. You can do multiple patterns in a single match, and the earliest, longest match wins. The earlier version of this was the one multiplexer, which takes a callback in a series of matches, and it's really not very elegant feeling. The first one to match wins, so it's kind of ugly, maybe not the most predictable thing in the world. One came first, and then multi-match came later, so one might get deprecated, but multi-match will stick around. So exec allows you to execute arbitrary commands. This one was also motivated kind of by conformance requirements, because we need to be able to, for instance, in the case of mailx, we need to see if it left dead letter around after the program is terminated, and I don't expose any I/O operations to the sandbox, just because I don't really see a need for that, and I think it would complicate things. So you could, for instance, use exec to execute test, and then see how that terminates to kind of be able to test that. That in some instances, depending on where that's located, that might complicate things a little bit more, since anything done as a result of executing. So you execute it, a callback is invoked, inspect the wait status, but you can't really do anything with that immediately after that's returned. So you'd have to enqueue another block in order to do anything with that. It's a little bit ugly, but in the case of something like mailx, it's okay, at the end of the program, I'm just going to check if it's there. I'll look at the exit status, and then I'm terminating either way in the callback for exec. So it kind of works out that way. And it could also be used for kicking off other activities that are maybe needed in the process. Pipe. This one is basically the same thing as exec, except instead you wire up standard out of what you're execing to the process that we spawned. So we p-open it, we read line by line. The script can apply a filter if it wants. So I don't really know what kind of things you may want to filter, but you can, and that's somewhat useful. And then it just writes them to the process. It's kind of useful if you need to do things like execute something else in order to, for instance, collect a password or something, as I had mentioned earlier. It might also just be for general fetching data from the disk. As mentioned, I/O is not available in the sandbox. And generally in the sandbox, you don't really have much of Lua. You have string functions, table functions, and that's pretty much it. Nothing else has been really useful in any of the scripts I've written. So as mentioned, signal handling, this was kind of inspired by conformance requirements. mailx specifically was the last one we dealt with. We've dealt with other ones in the past, but this was the most convenient example. And in the case of mailx, you get to the prompt, Control-C, interrupt one more to exit, send another one, see if dead letter exists. I have that as an example in the repository. We had already written a test in C for this, so I don't think that there's any point in deploying pork for that today, but it is an option if we need it. We can do pretty much everything we would need to do with the signal mask, and we can also ignore signals if we need to. It otherwise doesn't really touch the mask or anything coming in. So if you have any dependencies on any certain signal state going in, then you do need to actually set that up yourself. As far as debuggability concerns, it's because of the kind of weird nature of the scripts you're processing. I wanted to do something to try to make it a little bit easier to figure out what went wrong. So there's a fail callback that when a match actually fails, it'll invoke the callback with the remainder of the buffer so that you can write that out and try to understand exactly where you were. It's especially useful since you don't get any kind of output when it's running. It's fairly opaque in general. If you don't install a fail handler, then it just prints out some diagnostics, line number, basic information like that about the action we were trying to run, just to try to give you a hint of what you need to do next. And it also has debug and hex dump functions for outputting. So the direct execution mode was kind of inspired by Mark Johnston, because he actually deployed this in his testing tool called Bricolay. I think he's my only user, and he's talking about switching to Python. So that's we'll deal with that when it happens. But so in the lib version, you have a run script that you can use to just run a script, or you can spawn processes off with this. Pork.spawn actually returns a process object that you can do basically everything we had mentioned in the scripted slides. It retains all of the signal and terminal configuration functionality, but it also adds a bunch of SIG-IS functions that can be used to check the current status of all of that, since you're no longer operating in the kind of weird queued mode. So it's not anywhere near as limited. And this one will also terminate the process as soon as you try to close it for convenience. The notable difference between this and scripted mode is that there's no one action, only multi-match. It's kind of reflecting my desire to kill the one action, which I probably should have done a while ago, but maybe someday. And otherwise, it follows the exact same model. You write match to drive the process to completion, and you can also do other things like check the exit status, see if it was signaled or whatnot. And you can actually spawn multiple processes if you're using the library, so that's kind of convenient. One of my desires that I mentioned later is to kind of abstract out some of the IPC bits so that it's not all quite as tied to Lua, and then maybe write a Python version, just because I think that could be useful, especially with the blocking nature. I think that's a little bit handier than expect, and that could be a nice addition. It's not really on the roadmap anytime soon, though. As for scripted versus direct usage, the scripted usage was primarily intended for testing things. So this is what I would mainly use it for in, say, FreeBSD, for instance, while the lib mode was intended for arbitrary things. I didn't want to add the whole kitchen sink to it. So when I added it, I figured that anything else that someone wanted to add, they could just wrap the library, and then that's their problem to deal with, not mine. And I was picturing things like if someone wanted a mode where they can run it and actually have the user interact with it at the same time, or be able to interrupt themselves, that's the kind of thing you would use the lib for. So other things I added, I had a small talk with ChatGPT. Most of what it had for me was crap. Frankly, it had maybe 20% of its ideas were actually reasonable, and then I kind of beat them into something that kind of made sense. So the first one I had was porkgen, which is generally just for creating pork scripts. So it launches a program, it proxies its output to standard out, and then as you interact with it, it generates match and write statements, and passes your input through to the application. It does leave some previous match context just in case we got it wrong. Maybe, for instance, I thought you were responding to this, but you were actually trying to respond 3 lines up. So that's kind of handy. It's kind of expected that you will need to review and edit the output a little bit, but it at least gives you a nice start to a script rather than having to write the whole thing from scratch. So rpork, it's the R for remote, kind of self-explanatory there. It's just another executor. It executes the script locally, as you might expect, but every spawn command in the script is executed via the RSH program, which defaults to SSH. So this is kind of useful if you maybe design it for local testing, but you also want to try it on a different machine. So you can just use rpork and easily connect to a different host and just drive it all there. I mainly think of things like maybe I have a menu or something that I want to test on a remote device, say appliance or something. This kind of thing that I could do pretty easily with this. And it does do word splitting of the RSH program, kind of inspired by rsync. So that you can pass arguments to SSH rather than having to write a wrapper script if you need to do anything even moderately complex. So that's kind of nice. Another idea I had that I'm a little more interested in, but it's more complicated to manage, is pork fuzz, which doesn't sound very pleasant, but it's again exactly as it sounds though. Fuzz testing application input handling. I wasn't really sure of the best approach, but I kind of landed on something like you drive the program with write and match, and then eventually you just, instead of calling write, you call fuzz, and then we cooperate with something to actually fuzz the program. But this isn't really how fuzzers today work. What would be nice is something like AFL that has a server and then I can cooperate with it to launch the program so that I can still take advantage of some of the instrumentation that it would have done, but I can be consuming the input in Pork instead. But that's not really how it works today. So I'm not really sure how to implement something like this, but I would like to, and that's maybe a long-term goal. You can otherwise obviously just do your own kind of fuzzing, but it's not really as effective as the instrumentation-based stuff. So looking at some examples, this one is getting lonely one night, set up Netcat, listening on port 9999, and talking to myself with this. So as soon as it connects, it writes hello from the other side, and it matches anything and then talks back. So a nice little conversation with yourself, which is not really a useful example, but it kind of demonstrates what I think is a little bit of the elegance of Lua and writing something like this. So that's that example. This multi-match, which also isn't considerably more complicated. So this one is an example that you're intended to play with a little bit. You exec cat. So the first write generally dictates the path you're taking, and kind of a useful example to play around with the semantics there and get a feeling for how that generally works. So also not really a practical example, but something that can be useful to play with. And this one is one that we've actually deployed in FreeBSD. So this is some part of the testing that I was talking about earlier. So in this case, I've parameterized 8, 9 tests to this read size program that I wrote to make sure that we're getting file and read write for all of the different input. And I feel like this is a very powerful thing in general. This would have taken me a lot more C to write than just that amount for sure. And that's more or less it. As far as future work, I'd like to write more tests for interactive stuff in base. Right now we have the test for TTY stuff that I mentioned earlier. And we also have some basic, one test for T that I use it in, mostly for convenience, because you can stall the input to T, but it's much nicer if you can just have this TTY that you're not writing to and then send it as SIGINT. Then the libpork and Python interface I think would still be kind of nice to do, because Python can be more enjoyable sometimes. And then pork fuzz, as I had previously mentioned. And then that's it. Any questions? Perfect. Thank you.
Okay. Hi, everyone. How are you doing? Good? Me too. Okay. So today I'm going to be presenting S0i3 or S0ix on FreeBSD. And I'll start with a little bit about me. So I'm into like OSs and graphics programming. And I'm sponsored by the FreeBSD Foundation to work on this. And I also am a developer at Renewable, which is like energy storage solutions in Belgium. And I spend most of my time in a train. In fact, there's a running joke with my colleagues that I'm homeless because they only ever see me in a train. And yeah, so that's that. Once upon a time, a very long time ago, actually not that long ago, but computers used ACPI S3. S3 was a bit of a heavy-handed approach. You were just telling your computer, okay, go to sleep. And you know, there are other states that are still used today. So like S0 is when your computer's running, S5 is when it's off. And yeah, there's a few disadvantages to this. It's pretty slow to enter and exit, and it's pretty inflexible, and especially modern laptops don't support this anymore. So if you've got like one of the newer AMD frameworks, or even the latest Intel framework, I think, you don't have S3, and so you can't go to sleep, which is problematic for a laptop. So what is S0ix? So S0ix, you're staying in S0, and it's your platform that decides when enough requirements are met to enter an S0ix state and turn off the CPU. So the theory behind it is, yeah, you just follow some requirements, some device power constraints, and then your system will go to sleep. And so the holy grail of this is S0ix. That's what is saving the most power. That's when like everything is off. And yeah, so Ben Wadowski from Intel did a bit of work on this in 2018 with these two patches. But there was quite a bit of work to actually get it to work. So I want to start with a bit of a crash course on ACPI. I gave this talk at FOSDEM, at least this part of the talk at FOSDEM, so it's going to be pretty much the same. But yeah, ACPI is just, I mean, first of all, who's heard of ACPI? Because I feel like it's one of those things that a lot of people hear about, but don't know what the purpose of it is. So your platform exposes a bunch of information about your hardware, and it does this through this kind of configuration language called AML. And so, yeah, it's actually compiled. When you get it, it's compiled into ASL, and then when you want to read it, you decompile it into AML, and you do this with ACPI dump DT. And so here's an example for the lid device. So the lid device is just the thing that says if your laptop lid is open or closed. And you can see it has some kind of hardware ID and an object methods that you can query to know if the lid is open or not. And so this EWSL thing is just some like a register in memory, and it tells you if it's open or not. So it's pretty convenient because it means that you can just like read this AML and know like what should I read to know if my lid is open or closed. You don't have to like just happen to know the hardware address, or it's just a way to communicate what to read. And here's an example of how it's actually read in code. So this is ACPI lid.c. That's the thing that does this in C. And you can see it's just getting the integer. If there's a failure, we're just assuming it to be open. Otherwise, we get the status. If it's anything else than 0, then it's open. And if it is 0, then we assume it's closed. So hope that gives a bit of an idea of how that works. OK, next thing I want to show is the SPMC. So with S0ix, you have something called modern standby. And modern standby is telling your embedded controller, a lot of computers nowadays have embedded controllers, that, oh, this is a point in time where I'm going to start entering sleep, and this is a point in time where I'm going to exit sleep. And so your embedded controller will do stuff like on the frameworks, it will flash the power button slowly, so it indicates to the user that you're in a sleep state. But the SPMC doesn't actually put the system to sleep. So it exposes a device-specific method, and in ACPI, this is just like a multiplex function where like the first argument is like a vendor-specific, vendor-defined number, and there's a bit of vendor-specific complication, but for the most part, the important values are get device constraints, which will give you a list of device constraints you need to respect. and then display off and entry notifications to enter, and exit, and display on to exit. Right. So yeah, D states. So these are those device constraints. Your devices can have different power states. So D0 means that your device is on. D1 and D2 and D3-ish mean like sort of off. D3 is split into D3 hot and D3 cold. D3 hot means that it's off but still receiving power. D3 cold means that it's not receiving power. Sort of unclear what just regular D3 maps to. There's discussion with Intel about that. And yeah, to change the D state of a device, we need to talk about power resources. So here is the NVMe device and its power resources. Every one of these PR things corresponds to a D state. So PR0 would be D state 0. And it's saying that it depends on the P0 NV power resource. And the way that we know that we're in a certain D state is if it's the shallower states which have all its power resources on. Yes. So I have a little bit of a diagram to make this a bit easier to understand. So in this case, if the P0 NV power resource was off, then we'd be in D3 cold, because we're not in D0, not in D2, not in D3 hot, so it means that we must be in D3 cold. But if it was on, the shallowest one which depends on it is D0, so it means that we're on. So in this case, the NVMe device can either be on or off, depending on if P0 NV is on or off. Sometimes you've got more complicated situations, but most of the time it's pretty simple, like this. Right, so these are two patches to do that. And the next thing I want to introduce is suspend to idle, S2 idle. So all we've done at this point is just let the system know that we want to enter suspend, but we're not actually idling the CPU. We're not actually doing anything. And so, okay, let me read what I wrote. Yeah, our CPUs could still be doing work while we're in mod suspend, so we want to actually idle the CPUs. So the first step we want to do is bind ourselves to CPU 0. We want to stop the scheduler clock on all our CPUs. And we want to kick them so that they actually enter idle. We wake from this idle state from an interrupts, so we want to disable all interrupts, except for one kind of interrupt, which is the SCIs, which is the way that our platform lets us know that we're going to wake up. So this could happen if you hit the power button or open the lid or stuff like that. Yeah, that's interrupt 9 usually. So we stop all interrupts and we just allow the SCI, interrupt 9. So then we actually idle the CPU. We do this in a loop because our platform will sometimes send us SCIs and events which aren't necessarily wake events. So a common example is on the frameworks, if it's unplugged, every 60 seconds it will send you a battery status update. I'm guessing they do this so that you can track battery states while you're suspended. But we don't actually want to completely wake the system. So we do need to check whether or not this event is a wake event or not. And if it's not, then we want to go straight back into idle. So that's the S2 idle loop. Now, the one issue is that when we receive this interrupt, currently in FreeBSD, we don't handle this synchronously. We add this to a task queue, and then at some point it will be handled. So we need to drain this task queue, and I'm not really sure what the best way of doing this is. Maybe it would make sense to do this synchronously, to special case the S2 idle state, and then just special case this handling, and just do it synchronously right after we get the interrupt. But this kind of works for now, although it's a bit buggy. So yeah, once we exit the S2 idle loop, pretty simply, we just resume all interrupts. So we are how we were before, and resume the scheduler clocks. By the way, if any of this is a bit unclear, please let me know. Ask questions, because yeah. All right, so just idling is not sufficient for power savings. We actually need to enter, convince the platform to enter S0I3. And I don't know why I put this fun fact here, but yeah, dolphins and whales sleep half their brain at a time so they can still surface for air, which is something I discovered yesterday. I think that's pretty interesting. Right, C states. So we need all CPUs to be like in a deep idle state before the platform will want to enter SRI 3. And these states are called C states. So C0 is like active. C1 is what happens when you just do the halt instruction. And there's a bunch more. And yeah, depending on your platform, you could have more or less. In theory, the way that we enter this, and that's the way that I thought it worked for a long time, because that's how it's usually, how SRI 3 is usually introduced, is through the mwait instruction. So the mwait instruction, in theory, is just used to halt the CPU until a bit of memory is written to, and then it will wake it. But it can also be used to just halt the CPU until we get an interrupt, similar to halt. But you can also give it like a platform-specific C-state hints. So for example, you could tell it to enter C4 while it's waiting for an interrupt, and then to break out of that on interrupt. Now on AMD, that doesn't really work. So I have to do a bit of a quick detour to show you the AMD SMU. So the AMD SMU, I started writing the driver for this for debugging, mostly. It's like a small bit of the CPU. It's up here on the top, right? And it runs some firmware called PMFW, and it's the guy that's like responsible for doing all the power management stuff on your CPU. And it actually decides when to enter SRI 3. So this is the thing that we need to convince to enter SRI 3. We can send commands to it to get like residency information. So residency is just how much time are we spending in a specific state. So that's pretty useful to know if you actually did enter SRI 3 or if you were just active during the idle period. And you can also hint it that we're entering and exiting sleep, which you need to do, otherwise it will never enter SRI 3. So the driver that I wrote for this creates sysctls with these residency stats. So let me see if I can select this like that. Where's my cursor? There's my cursor. So this is the output if we haven't gone to sleep yet on the system. So everything is predictably 0, except for USB 4.0, which always seems to contain junk for some reason. Yeah, it's a bit of a weird thing. Right, so if we just do mwait, if we just try to idle and sleep with mwait, AMD SMU will show that the CPU was still active during this, and it will give us time spent. The time spent will entirely be in this SW drips thing. So I guess this is a bit of a misnomer. That's just how it's named on Linux, but this just counts basically between when you tell the SMU that you want to enter SRI 3 and when you want to exit. And then it will give you a bunch of dependencies that need to be met before it will actually do it. And so in this case, it didn't enter SRI 3 because USB 3.1 and USB 3.0 were still active, and the CPU was still active. So this is USB 4 related. I know it says USB 3. It's USB 4 related. I'll cover that a bit later. But the CPU is the thing that we'd like to cut down on first. And so clearly mwait is not sufficient. That's what the SMU is telling us. We have in ACPI this CST object. CST thing gives us all the C states that our CPU supports, and also an entry method. So it just gives us like these registers, and when we read these registers, then the CPU in question will enter that C state. And there's, I guess the equivalent to this is LPIs. LPIs basically have the same thing. It's just that some newer systems don't have CSTs, and some older systems don't have LPIs. But it's the same idea. And what did I write here? Oh yeah, that's just saying that, yeah. The LPI things can contain a resonancy counter, but this isn't used on AMD, so let's just forget about that and use the AMD SMU. Right, all this is in ACPI CPU.c, and for some reason, which I haven't quite figured out yet, John and I theorized that it was related to S3 entry, there's this disable idle function that's called when you suspend the ACPI CPU device, which prevents this C state entry. So yeah, if we want to enter SRI3 and we want to like actually suspend the CPU, we need to prevent this somehow. So for now, I'm just special casing it, but I need to figure out like what the purpose of this disable idle thing is in the first place. And so if we do this, now the SMU tells us the following. It says that the CPU is not active anymore, which is very good. But there is one thing that we're missing, and that's these things, the 3.1 and 3.0. These are still active. That's the USB 4 stuff. So that was a lot of work. Like a large part of the work of this project was actually writing a USB 4 connection manager to turn this off. So here's a bit of a quick overview on USB 4. So USB 4 is kind of this thing to tunnel other protocols. It's not like a USB in itself. Actually, when you're using USB over USB 4, you're just using USB 3.2. That's just tunneled through it. And so here you can see like the diagram of the host router. This is just like stolen from the USB 4 spec. All USB Type-C connectors, actually I have this on the next slide, have these middle pins here over which USB 2 goes. So any kind of USB 2 stuff will just go straight to the USB-C connector. It doesn't have anything to do with USB 4. But over here, USB 3 stuff can either go straight to the Type-C connector in the case of like in fallback mode, essentially, or it can go through the USB 4 router, which can then decide to use the pins that USB 3 would otherwise use and tunnel that data over that. And it can also tunnel different types of data, like DisplayPort or PCI. Now, you might have realized that on the frameworks, even though we don't have USB 4 support yet, I mean, not for DisplayPort at least, DisplayPort and the HDMI thing will still work. That's because there's a special mode called DP alt mode, where, yeah, there's negotiation happening over the sideband pins, as far as I understand it, and then the DisplayPort signal is over these pins here, which are otherwise used for either USB 4, either PCI, or USB 3. So yeah, that's a rundown of that. Now, I inherited the USB 4 code from Scott Long, who wrote like a skeleton of it a while ago. And this was transferred to HPS. And yeah, so I picked this up. I removed the ICM code. So ICMs were, that's an internal connection manager. This was, yeah, basically a big part of the driver was implemented in firmware, but this was a bit like, a bit odd because every single like controller had its own like quirks and idiosyncrasies. So yeah, Scott Long kind of suggested to axe all of that, since anyway that's just a bunch of old controllers. And now we're just entirely using the HCM, which is the host connection manager, which is completely OS side. Now the reason why we need to do this USB 4 support is because in the BIOS there's such a thing as a pre-OS connection manager. This is just used so that USB 4 works in the BIOS. But it means that when we start up our OS, we don't have, I mean, the USB 4 routers are not in a D-free state, which means that we're never going to be able to enter SRI3. So I did try one thing, is to pass the USB 4 like controller to a Linux guest to suspend. That just miserably failed. But yeah, so I had to start actually picking up on that code and writing the suspender routines. It turns out it wasn't too complicated. I mean, there was a bunch of like code surrounding it that was a bit complicated, but the routine itself is pretty simple. Since we're not doing any links, we don't really have to worry about link states. I'm assuming they're all like by default in CLD. I'm not entirely sure of that, but you know. So all we really need to do is pretty straightforward. There's like a configuration space on the routers, which we can set the SLP bit in, which is like sleep bit. And then we just have to wait for the sleep ready bit to be set. And once that's set, then we know that the system, the router has gone to sleep. On like V2 routers, it's a bit different. We can still do it like this, but the proper way of doing it is to wait for a notification instead of just polling this bit to see when it's set. Sorry. All right. So now that we do all our USB 4 stuff and we put it to sleep, the SMU tells us the following, which is that not only our USB 4 stuff here is set to 0, which is correct. This is still garbage, I don't know why. But that we also have time in SRI 3, which means that our system is actually entering SRI 3. And this thing here, the last entry status is set to 1, 2. So yeah, that's that. Yeah, so I just wanted to thank Mario Limoncello because during the development it helped a lot. He helped me a lot getting like a very minimal Linux kernel built so that I could test, try removing stuff to see if it actually impacted SRI 3 entry on my framework laptop. And he has a script actually for this AMD S2 idle, which I'd like to port to FreeBSD, which diagnoses reasons why your system wouldn't want to enter SRI 3 for you. So yeah, this was pretty useful. He was very helpful, so thanks to him. All right, yeah, there's a couple more things I want to say about USB 4. Did I forget about them? I forgot about them. Okay. Right, testing. Please test this. You can apply each revision with argpatch, no branch. The tip of the SRIX and S2 idle stuff and the AMD SMU stuff, they're all in one big stack, is over here. USB stuff is over here. Now this is just supporting the pink sardine controller at the moment. We need to add more generic support, but right now it's just pink sardine. Pink sardine is the one that's in the 7000 series AMD framework laptops. And there might be a way to apply all these changes at once, but I don't know Arc well enough. So I also have a simple branch on GitHub that you can just clone over there and then build it as is, and it should work. Except that at the moment I just rebased it on 15, and it breaks, it kernel panics all the time. I think I found the reason why it kernel panics, but it's, yeah, I haven't fixed it yet. I had this genius idea to rebase right before this talk, so. Right, so yeah, please test it on your machine. Make sure that you have S2 idle on your machine once you build all these patches. It should just work, but this is a good way to know if you've applied everything correctly. You'll go into ACPI supported sleep states, and these are the states that are supported. On older computers with S3, you'd also have S3 here. S0ix does work on a lot of S3 computers, so you can try doing that. And for modern ones, you'll just have S4, S5, and S2 idle. To actually use it, you can set the ACPI power button states to S2 idle. That means that when you press the power button, it will enter S2 idle instead of the default, which I think is shutting down, if I'm not mistaken. There's also an equivalent for the lid. So that's lid button state. And yeah, if you do manage to do all that and you do manage to suspend, please send me the dmessage, ACPI dump DT, and if you're on AMD, the contents of the AMD SMU. And that will tell you if you actually entered sleep or not. Currently, there's a bunch of issues where, especially USB 4 related issues, I mean, it's very buggy at the moment. It breaks a lot. There's a lot of random panics and stuff like that. And it won't re-enter sleep once it wakes. So the USB 4 router will sleep, wake, and then not re-enter sleep. I think I know why. I am in the middle of fixing it. So yeah. All right, here is the 1/3 chance of failing demo. Unfortunately, the HDMI on my framework doesn't seem to be working with this thing. So, oh yeah, I lied to you guys. This isn't a framework. It's a Mac. It's my backup. This is a framework. So, hold on. Let me put the backlight back up. So I'm going to try to suspend it. I think it will panic. I'm actually fairly certain it will panic. But, you'll see it here first. I'm going to press this button here. And is the cursor blinking? It stopped blinking. It's not entering suspend. That probably means it panicked. So I had prepared a list of jokes to tell in the case that it did panic, so that while I waited for it to reboot and you know, I could tell a bunch of jokes. But now, since I'm just running on the backup computer anyway, I'll leave the jokes for last. You can still hear the jokes later. Yeah, that's all. Okay. Oh yeah, one thing to note also, do remember when you're testing to unplug your computer from AC, at least on the frameworks, because it will, like every second, send you status updates when it's plugged in, and it will never enter SRI3. So it needs, oh, the screen went black on the framework. It's still not suspending, it's just, oh, it rebooted. Okay, anyway. Future, so I haven't done anything for Intel yet. It might just work. Someone told me it works on their Intel. I don't know if that's true. I haven't had an opportunity to try it. I need to fix the USB-related panics. I mean, it's a big amount of code all at once, so there's a lot of a lot of stuff to fix and to smooth out. I'd like to be able to give the ability for users to add more complex wake rules. That's not something I really covered, but currently, so you can tell like different devices. You can tell ACPI, okay, I want this device to turn on to wake the system, or I don't want it to wake the system. So an example could be like maybe I'm plugging a device in and I want this event to wake the system or not. Currently, it's broken on a lot of modern ACPI stuff. Yeah, and the last thing is, no, the other thing is S4, suspend to disk. So this is, so S3 and SRIX, all this is doing is suspending to memory. Everything turns off, but the memory is still alive. So when you turn it back on, it just works, I guess. With S4, you're actually copying your memory to disk, and you're basically shutting down the system. And then when you wake it, you're rebooting the system, restarting all the device drivers, and then copying that memory into memory. And it's pretty good because it saves much more power because you're basically entirely off. No, you are entirely off. The only issue is that it takes, as you can imagine, a long, long time to enter and exit because you have to, copy all this data in and out of disk. And so usually what you want to do is when you're in a state like SRI3 or S3, you want to wait a certain amount of time. And then if the user hasn't touched their laptop in like 2 hours, you can probably safely say that in the next couple minutes they're not going to open it. So you can go into hibernate and then save more power. And then next time they open their laptop, it will take a longer time to start up, but at least they'll have saved, you'll have saved quite a bit of power. Last thing is idleness determination. I'm not really going to go into that. Right, another thing I wanted to highlight, there is a GSOC project that I'm mentoring this year on bringing PowerTop to FreeBSD. So PowerTop is a Linux tool which gives you a power usage breakdown of all your processes. And yeah, it would be cool to bring this to FreeBSD. And yeah, Sai is working on this. Yeah, so this is part of the Foundation's laptop project. There's an issue tracker for all things related to this. Please do test this on your laptop if you have a chance, and send me an email if stuff isn't working, or is working. I'd also like to know what is working. Yeah, that's pretty much it. I think I covered all I wanted to cover. So here's my contact information. If you'd like to have a beer with me, or 12, you can. Here's my FreeBSD email, regular email, website, GitHub, and Discord, but I don't really use that. So yeah, that's about it. Now, would you like to do the questions first or the jokes first? Because I have a few jokes. Not that many, actually. I have like 4 jokes. OK, I'll do like 1 joke and then 1 question. So I just built an ATM, which only dispenses coins. I think it just makes sense. Because, OK, questions. Who wants to ask a question? Yes?
Does that S0x state similar to S3 in a point that we should suspend all devices? Do we depend on all devices, device driver properly suspend, suspend resume?
Not necessarily. I think there is, I'm I'm not entirely sure if the Wi-Fi driver, you have to completely shut it off, and if it still will wake the system, because there's I forget what it's called, but there's a mechanism whereby if you can make it so that if you receive a packet that's important to you, your Wi-Fi chip can wake the system or not, which could be useful if you like, I don't know how deep it really goes, I haven't really looked much into this, but it could be like maybe you receive a packet from a certain IP address, then you wake up or something like that. I don't know if you have to turn the device completely off for that or not. But either way, you have to respect the device power constraints that the SPMC gives you. And you are free to, if it tells you that you don't need to put a device into S3, you are free to leave it in, if it tells you don't need to put a device in D3, you're free to leave it in D0 and still have it, do whatever kind of stuff you want.
But do you call all the suspend methods for all the device 3?
Currently, yeah. Yeah. But yeah, in theory, if it doesn't tell you have to put it into D3, you can leave it in D0.
So you showed how USB 4 also tunnels PCI Express. What happens if there's a PCI Express device connected via USB 4 and is on its own power supply? Will it be also suspended, or will it hold up suspension?
That's a good question. I assume it kind of depends on the device. I mean, from USB 4's point of view, as long as you sleep the lane that is sleep the connection, then that's all your host is concerned about. I'm not sure how devices handle that, if they stay on, if they're on a different supply, or I don't know. At least I think if you're turning off the lane, it's not getting any power from the host.
Yeah. And would that be any different with Thunderbolt?
Thunderbolt is, USB 4 is, that's sort of the same thing. Thunderbolt is like an older version, I guess, that's proprietary, and USB 4 is just the standardization of Thunderbolt.
And both tunnel PCI Express identically?
Pretty much, yeah.
Okay. Thanks.
Yeah. Anyone else? Okay, I guess it's time for another joke. So I got a pen that writes underwater. It can write other stuff too, because it doesn't only write underwater. Okay. Right. Any other questions?
All right. So we have a couple questions from IRC, but before I get to that question, so you had displayed the info about the laptop desktop working group. Just so everyone else that GitHub is as far as I can remember, the comments are kind of like you have to ask the foundation for comment access because reasons. So you're probably better off subscribing to the FreeBSD desktop mailing list and kind of following along to the monthly meetings. And because obviously the mailing list is the mailing list, and right. Anyway, so now we have some questions from IRC. What is still missing to support PCIe hot plug and unplug via USB-C?
A lot. The USB 4 stuff at the moment is really just enough to initialize the router and suspend it, and already that's like 7,000 lines. So there's a lot of work to be done to get to any kind of useful stuff with USB 4. I mean, for now, my main concern is just getting it to the state where it can suspend. Maybe I'd work on USB 4 in the future, but that's not in the plans right now.
All right. Okay, the next question from IRC. What's expected power consumption if you get into S0IX compared to S3 or S4?
It should be identical between S3 and S0i3. S4, the expected power consumption is basically 0. The only thing that's still running is your embedded controller, as far as I know, which is necessary for handling stuff like, when I press the power button, what do I do? So yeah, S4 is basically 0. S3 and S0IX are pretty much the same. They consume less, but not none.
All right, and then what is missing to use common USB-C or Thunderbolt docks with FreeBSD laptops?
Same answer as the question earlier. Everything's missing. I mean, we need For docks, I mean, if you want to support everything on a dock, and you want to also support like devices downstream of those docks, you need to support DisplayPort over USB 4, USB over USB 4, and PCI over USB 4, which is a lot of work that's just not existing. Yeah. Any other questions? Okay, well, I think that's about it then.